Ja, ja. 1, 2. Ja, ja. 1, 2. Sieht gut aus bis jetzt, ja.
So good morning, everybody. So thanks a lot for coming. I know that's kind of a big thing in these times, and I think we also have many who couldn't make it, and mostly because of COVID. And I think it's probably not the usual case, but I would also like to first thank the organizing committee here and the technical people and who made all that possible. I think you can imagine what the dynamics was in organizing such an event, and that you need a lot of improvisation skills to actually go across that. So lots of thanks to them who made that all possible. Right. So the reason that we are actually here and that I wanted you to be here, and I think it's kind of many colleagues and many of us work together in an open research environment, exchange code, and work together, is that lab is not kind of a lab that we want to just have for ourselves, but we would actually like to share it more with the community. So we made a lot of effort in, for one thing, building a cool lab here, but also to have the lab as a digital twin and to have it downloadable. So actually what we want to have is that people in the community can actually download the research lab, and I will basically talk about that later in my talk when I actually introduce that. But I think that's kind of the main thing, and I think robotics is a very cool area, right? So it's kind of, this is kind of the lab is supposed to be a small step towards that goal. Yes, so I think it's my pleasure to introduce Professor Jutta. Oh, yes. Don't. Günther, yes. So finally, yeah. Yes, and so she's the new rector of the university. She's in acting rector just for a month, right? But Professor Günther is extremely supportive for our activities. Part of the team helps us in everything, and of course, kind of getting her here and actually welcoming us to that event is again kind of a very good, cool contribution to our work. So yeah, Jutta, please kind of give your address, and thanks a lot for being here.
Yeah, thank you, Michael, for introducing me. I don't know if you can hear me well enough. I can do it without the microphone, I think. Yeah? Okay, for the streaming. So I will use it. Yeah, no problem. So, yeah. So, dear Professor Beetz, lieber Michael, dear colleagues and friends of the community, it is my great pleasure to welcome you today here at the Institute for Artificial Intelligence. Preparing breakfast or lunch, mapping an area, scanning shelves in a retail store. These are only a few everyday activities which the robots here at the Institute for Artificial Intelligence are able to perform. These are also activities that are closely linked to challenges in the society. For instance, in the field of healthcare or in the field of the retail sector. Here at the Institute for Artificial Intelligence, researchers are so dedicated to addressing these challenges by developing new solutions, right at the intersection of robotics and artificial intelligence, which means cognitive robotics. This institute is very successful. It has won several awards. It has won the Technology Transfer Award from EU Robotics in the category of Best Academic Research Institutes. Furthermore, the startup Ubica, which is a partner of the institute, has won the German Science Award for retail in the category of Best Startup Activities. The institute is a member of a European Network of Excellence in Robotics, EU Robin, as well as the EASE Network, which is a prestigious collaborative research center funded by the German Research Foundation. So these are only a few of the big successes of the institute and the big efforts Michael and his team is doing. Because of this, the institute is really the ideal place for setting up the laboratory on artificial intelligence and robotics to run experiments for cutting-edge research. As a president of the University of Bremen, I am of course very proud that tonight this laboratory will be opened. It will be, of course, a core facility for basic research, but also serve as an innovation leader for Bremen entirely. And in this sense, it will play an important role for the transfer activities of the University of Bremen, as well as for the artificial intelligence strategy of the federal state of Bremen. Furthermore, the laboratory will also train motivated students and young academics from all over the world to become experts in this important field of artificial intelligence and robotics. What has always fascinated me when talking to Michael and his team is that the institute has a very strong belief in open science. Open source and open educational resources, from my point of view, are the best answer for a complex world and for a densely interconnected world. It is my pleasure to open the two-day conference today with you, which took so much effort to organize. I could observe all the activities and the dedication Michael and his team preparing for this day, for today and tomorrow, to have you all. Today, the program will include 4 sessions with scientific talks, so given by researchers from this very interesting community of artificial intelligence and robotics. And tonight, the new laboratory as a new facility will be opened. Tomorrow, the day is devoted to discussions and keynotes from industry to better connect industry and science here on the campus. I would like to thank you very, very much, Michael, and your team, that you have made it and that you took the effort to organize this high-level event today. My congratulations to this, and I wish you all a very interesting conference with a good exchange and good talks to each other, discussions, and make use of the possibility to network, etc. Thank you very, very much, and have a great conference.
I think we are going to continue with our program. And yes, as it is in these times, our first speaker, so we had to rearrange the program because of COVID, and because of kind of illness. So we have to postpone the presentation on the European Network of Excellence Centers in Robotics that Aline was supposed to give into the afternoon, and it has to be given by Daniel, who will kind of step in. And our first speaker is again sick because of COVID, and this is Giulio Sandini. So, but Giulio has sent us kind of his talk as a video lecture, so we will play the lecture and we basically get his view on the field. So let me just briefly say why it was so cool to have Giulio here, or kind of as one of the participants. So Giulio, he's one of the kind of very first people in the European robotics community who has started the cognitive robotics and cognitive vision community in Germany, in Europe, right? And so he was leading kind of very impactful projects. So he was having one big community project, which is the ICAP robot, which is a small 3-year-old robot, which is supposed to learn social capabilities together with humans. And he has built kind of a community around it. So we will have Giorgio Metta later. He's now kind of the science director of IIT, and they together built that program. And what is also important is that they also build it as an open research, open source community. So they were building kind of the YARP software for robotics based on that. And and Giulio, he's continuing to push these ideas of cognitive robotics, having cognitive architectures for robots, and now he starts soon here.
Genova, and I want to welcome you at IIT. My name is Giulio Sandini, and today I'm going to present you the outline of an open initiative I'm proposing at IIT, an initiative called ICOG, which stands for the ICAB Cognitive Architecture. The outline of the talk is here. I will start and I will spend quite some time explaining why I think it is important to initiate now an activity toward the realization of a cognitive architecture. I will then talk a little bit about the goals of the initiative, and finally presenting the initial plans, at least for the first year, with some details. When you talk about cognition, I think it is important to start with some definitions, just to explain a little bit what we think about, for example, a cognitive system. So for us, not only for us, a cognitive system is an adaptable system which is able to act predictively using a core of cognitive abilities, what are called the cognitive abilities, such as attention, learning, memory, decision-making, reasoning, and so on and so forth. I mean, it is a predictive, context-sensitive way of acting. Okay, so the cognitive architecture, in fact, integrates these cognitive abilities in such a way that they are coordinated and they are selected on the basis of prospective decisions. And so it is a prospective control of the action that are required to achieve the goal. And this cognitive architecture can be implemented as a dynamically adaptable software framework embedded in a physical body, like the one which is graphically sketched here. You know, core abilities, the body, the environment, all these aspects need to be taken into consideration. So why a cognitive architecture, and why now? You know, what is important? What is the special time? You know, well, I will address this issue from 3 points of view: from the ICAP point of view, from the industries, and from science perspective. Starting from the ICAP strategy, you know, advance the ICAP strategy. So the ICAP strategy, in fact, started in the Robotics Lab project, and the main important point of the project was that the project had two goals. One was to create the ICAB, the platform, the humanoid platform, but the other joint goal was to advance our understanding of cognition. ICAB was designed and realized to drive research on cognition. And the activity was divided, building the platform, doing research, but also building a community. ICAB has been is an open source project. The other point of the RobotCab was that it's a multidisciplinary approach, working around two concepts: development of cognitive abilities and mirror neurons, or related to the internal models that we have in our brain. So, of course, we also address the issue of cognitive architecture, sketching it into different schemas along the execution of the project, and ending up with an architecture described extensively into a book by a computer scientist, David Vernon, a developmental psychologist, Klaes van Hofstede, and a neuroscientist, Luciano Fadiga. So, condensing what we were investigating about cognition into a multidisciplinary book. So the ICAB adventure today is certainly a success. I mean, we have a lot of friends. There are more than 40 ICABs in the world where people are working and producing results. We have collected a lot of software, more than 15 million lines of code from all over the world. So this idea of a shared software, open software, is working. We have published a lot of papers. If you look at the database of the IEEE publications, you find only on IEEE publications, 52 journal papers, 453 documents, which includes proceedings of conferences and other important related things. The only bigger number is the number of now robots sold, but the cost of a now robot is about more than 1/50th of the cost of the ICAB. So, and it is used also for research which is not related to cognition. Last but not least, the adventure of ICAB has produced the ICAB Tech, a unit of IIT which can produce, develop, disseminate, and collaborate with research centers all around the ICAB. This is a very important result of the ICAB adventure, which has been possible only because of the existence of IIT. Of course, I mean, these a lot of papers have produced and are describing a rich collection of behaviors and abilities designed by researchers. I mean, here are some researchers at IIT, but of course there are many others around the world working on recognition, reaching, gaze tracking, balancing, touch, affordance, all these topics which are the seeds of the cognitive architecture. But we are now at a critical point, because this fragmented approach, even if very interesting and advanced science, does not scale toward a system, an adaptive system, does not work toward an intelligent system. So there is a limitation. here. It is, is like the Swiss knife. It's a good idea. Then you can improve the idea a little bit more. But this does not work. I mean, this adding one tools at a time is not going to produce an intelligent system. You need a big picture. You need to refer to a big picture. We don't know the picture, but we should start thinking about the structure. We need to have an architecture as a reference where to insert what we do. So we need to refer to a cognitive architecture if we want to continue this ICAB strategy. The second point is industrial. Why we need a cognitive architecture to foster new robotics industry? Well, first of all, we need to stress the fact that we are dealing with a special kind of industry, the industry building robots collaborating with humans, different ways, different for different applications. And in some sense, we have to ask ourselves if we are not promising too much too soon now, and I base this doubt, on the fact that while robots in 40 years have improved their athletic abilities immensely, they went from a hopping robot to something like the Atlas robot here. There is still a big mismatch between the ability to act and the ability to understand. These robots do not understand what are the goals of the actions performed by humans, and at least in the general sense, there are examples related to individual abilities, but not with something that can grow in time. So we have a strong, our robot have a strong, agile body, but really still a weak and clumsy and clumsy mind. And this is slowing the growth in the field of social and personal robot. There has been a lot of publications going on trying to understand why commercial activities addressing social robots didn't make it, and these failures are due, in my view, to exaggerated expectations about robot ability to understand, not robot ability, let's say, athletic or moving ability. So social robots need to relate to humans, starting to relate, being able to relate to humans. And by that, I mean robots should be able to understand humans and to anticipate their intention. They should be able to answer questions like this one: how would a human behave in this situation? And this is not only true for the ICAM. If you take an autonomous car, the autonomous car moving in a road populated by pedestrians and other drivers has to ask itself the same question: how would a human behave in this situation? So we need to go beyond real time. Robots need to go beyond real time, beyond this famous action perception loop. We need to add intentions to the equation, and we need to add experience, the ability to acquire experience for a robot. And you end up with a different loop. You end up with a loop where you start predicting what is going to happen in the future and explore to see if your predictions are true. We always have a goal in mind, and this is a loop is repeating itself. And in order to study this loop, we still don't know how this loop works in humans. So we need to develop to develop social robots, we need robots need to be able to act prospectively, and to do that, we need to study humans' internal model. We need to understand how human brain is working in this respect. And neuroscience offers theories like the mental simulation theory of Marc Janero or the mirror neurons approach of the Parma group as a starting point to investigate these aspects. So again, we need to refer to a cognitive architecture as a whole. Knowledge, of course, knowledge is still missing, and however, our understanding of some of these scientific issues today has matured, both in the area of computer science, cognitive neuroscience, artificial intelligence, and it looks like there has never been a better time to try to make a big push on this, Also considering that this big data approach is only part of a solution. We still need to add more to that. We need to study cognition producing a lot of science loop. Of course, this idea of an open, this idea of a cognitive architecture is still an open issue. It has been investigated for about 40 years now. I mean, this is a recent paper published 2 years ago, basically describing more than 80 cognitive architectures developed in the last years. And ICAB is more or less here around 2004, 2005. And of course, not everybody has the same idea of how to implement a cognitive architecture. In fact, there are, at least three different approaches, the emergent approach, the hybrid, and the symbolic approach. Of course, I cannot enter into the details of this architecture, but there is a lot of research already done, a lot of groundwork already developed, not only internally but internationally. But why is this a strategic initiative for IIT now? That's the point. And I have 4 points to describe this strategic initiative. First, this initiative, it fosters multidisciplinary convergence. This idea of the ICOG is a challenge which is common to engineers, neuroscience, philosophy. So it glues together different communities, which is what we need now. Not only that, it addresses the issue at the abstraction level, which is common to everybody. It's not molecules, it's not closing the loop in real time, it's not about understanding only understanding humans. So it's a mix. It's not like the brain is built, but everybody can talk about and can exchange information at this level of abstraction, which is fundamental if you want to build a multidisciplinary group. It is driven by a human-centric approach. Even if the cognitive architecture can be seen as in animals and not only in humans, certainly ICOG and what we have in mind captures the essential characteristic of human cognition. And the fact that it is human-centric, it is another important aspect in relation to the outcome of possible technologies along the path. Last but not least, it targets a novel educational area because the study of ICOG is a team effort. And as such, is an ideal arena where to train young researchers to work in a multidisciplinary environment, which is not so common as people usually think. So ICOG is a means. It's important to mention it's not an end. We have to create an architecture, but also we have to advance our understanding of the key issues of cognition. We are working on the principles of cognition so that they can be then exploited in all different areas. But it is important to think at ICOG as a mean, like ICAB has been, a mean to study cognition. So the goals of the initiative, 3 simple goals. First is to create an extended research community in IIT for the reason I was mentioning before. The second is to implement, test, and share the core components of the architecture. And third is to expand, this IIT-centered ICAP community, by establishing a network of international labs working on cognition. And this is the ICOG extended community, potentially extended community at IIT, which I see as a federation of individual groups, each one maintaining its specificity. And if you look at the names of the units at IIT, cognitive appears 4 times. So it's really implicitly a core of IIT activities, and of course it has a very interesting and potentially very powerful link with other IIT initiatives like the Robots for Better Life initiative that has been proposed by Antonio Bicchi. The second reason why IIT is in a very advantageous situation is the fact that we have this ICAP Tech organization. We have the infrastructure to collect contributions from different groups and glue them together and produce something which can be shared effectively with other researchers. Last but not least, we are advantaged with respect to the other research centers in the world because we can build on our existing network. All these points represent an ICAB sitting in one of the labs. Well, there may be an error here because these 2 points cannot be. We don't have ICABs floating in the sea. So these two are one in Japan and the other one in Korea, in fact. And I already spoke with David Vernon, who is a long-lasting friend of ICAB at the University of Bremen now, where Michael Betts is proposing a very interesting cognitive architecture called CRAM, and together we can start building this community as together with David and Giorgio Meta, we started building the ICAB existing network many years ago. So the initiative is very general. Cognitive architecture is the necessary base for any artificial system to interact safely with humans in human populated area. So in this area of cognitive engineering, what we propose is very critical, is very crucial. Plan, still a sketch plan. So first year is going to be knowledge sharing and building. A lot of activities, detailed for the first year, discussing specific cognitive architectures and key challenges, brainstorming about basic knowledge, formation of a special interest group, discussing about the scenarios where we want to target to exercise the ICOG. We need to find and to imagine a scenario where to do that. We want to build a live infrastructure with a live repository of shared knowledge and start establishing the basis for international collaboration. So the second year is knowledge consolidation and activity planning with the first basic modules of the cognitive architecture. The last, at least so far, year is going to be devoted to presenting the first example of the architecture and devoted to the consolidation of a multi-year planning of research, to contribute to the new IIT scientific plan and to prepare for international projects supported by external sources, because as we all know, good research has to be funded reasonably well. So the first year results, and this is my last slide, are listed here. It's just a promise here. I know that next year I will have to go through all these points if we proceed, but I think this can be done. So building the group, coming out with first hypothesis of the cognitive architecture, have completed the live repository and infrastructure for shared knowledge, discussed in depth about possible scenarios and the outline of 2 or 3 years activities, just the outline, and establish the basis of international collaboration, which implicitly includes also the analysis of the existing external funding. So these are the goals, the expected result, the results that I expect for the first year. And with this, I thank you very much with this last slide. Thank you, and thank you to be with us.
I think we can now have a short coffee break, right, Hagen? Or what? Could we have I think it's probably, and then we continue with Kay, right? And yes, and we are looking forward to that. But I think first coffee for everybody. yes, we are starting our next session, and our first speaker will be Kei Okada. So Kei is coming out of the probably oldest robotics laboratory in Japan. So it was originally founded by Professor Inoue, then Professor Inaba, and Kei, and I think it's just an amazing lab, right? So when you go and you see the videos, it's about every doctoral student building their own robot, right? And kind of the basic software of the robot, and the variety of robots the lab has developed over the years is just amazing, right? And of course, kind of, if you have such a success in robotics, that can only be the case if you're using the right programming language, and this is, of course, Lisp. And so I think the JSK lab was also developing their own Lisp dialect and building their system on top of it. And I think it's kind of the other thing is that the JSK lab is really one that is very open, inviting, and Kei, I think, is the one. So for one thing, they were partner in the PR2 program, and also had the PR2 robot, and also Kei started the ROS community in Japan, right? And kind of we have co-advised a doctoral student, and we had a long time together, and I'm very happy to have you here and hear what you have to say. Thanks a lot for being here.
Thank you very much. Can you hear me? Okay. Yeah. Okay.
You should take off your
Oh.
mask now, then we understand you better.
Okay. Thank you very much. So here's my today's talk title in the brochure, but I want to slightly change the title from socializing robot towards not robots in everyday life, but everyday life with robot. And I will explain why I want to change the title in this talk. So here is a slide that I always used in my talk. And as you can see, we are called JSK Laboratory, and there's 2 professors, and now we have 7 young associate professors, postdocs, and we have about 40 students here. So this is very big laboratories. And in this laboratory, we are doing the building robot and utilizing robots. And in the building robot section, as you can see in the left, we built a human-like robot, musculoskeletal robot like this. And in the utilizing robot team, we use a robotics platform like Michael's lab. We use several kind of the robot platform and building the robot systems that can help our daily life like this. So this is our goal or motivation or doing the humanoid research or robotics research. And I think our uniqueness is system integrations and real-world applications. So you can see here left, there is a lot of robot, and this is part of robot platform in our laboratories. So I say that we have 40 students in laboratory, and maybe we have more robots than students here. So each robot has at least 1 robot and doing some kind of researches. And I think one unique point here is we have a lot of different types of the robot, but we want to build the one robot system that can deal with different types of robot in different types of tasks. So we are building the, and on top of that systems, we use Lisp languages because, as Michael said, Lisp is the best language, I believe, in the world for the robotics research. And we built the direct code, use Lisp. And all of the robot here is modeled in the Lisp languages. And we use a different level of the modules, intelligent modules like recognition, control, reasoning as a, how can I say, a ROS node. So most of the software developed in our laboratory is open source in the GitHub. So if you are interested in, maybe you can check that repository here. And also, we are focusing on real-world applications. And we also use, of course, simulations to test our software algorithm. But even if we are able to run some software or some algorithm or functions in simulations, it is very hard to convert that one into the real world. So I think this is not the simple sim to real problem, but there is something that we are still difficult to model in the, how can I say, mathematics or simulation, what's happening in the real world. So the real world is more than just a physical simulation, but it contains a lot of different things like frictions and some system failures, or also there are some interventions from the humans or other agents. So we are always try to integrate the system and apply robot in the real world. Okay, so this is knowledge representation used in our laboratories. And so I think this is very, how can I say, people in this community are interested in how to represent the world and how to build the knowledge for the robotic tasks. And this is a 3D graphics, but the Lisp language that we are using is called use Lisp, and the one big character of that language is it has a 3D geometric modeling features. That means that we can build the 3D models as a first-class Lisp object. So each object in here, like robot, and you can see some kitchens and the plastic cup and cups and table, all these objects are instance or object of the Lisp language. So this is why we can manipulate these objects in the robot knowledge representation and perform some infer or some planning within that. So this is how we build our systems. And here, we show some recent activities on expanding our knowledge representation. And this is our effort to integrate sound or acoustic knowledge with the task-related representations. And here we see a robot moving around the house environment, and we make label for each sound. Like this is a sound for a kettle is beeping, or if the door of the fridge is keep opening. I don't know about how Germany fridge works, but in Japanese company, there some functions that if door is opening for some period, it starts beeping, and then it notifies us we have to close the door. So we have some data for the such sounds, and we connect that knowledge of sound label and the actions that the robot have to do. So here the robot sees, if robot sees the sound of the kettle, then robot stops the oven of the stove, and also robot sees the sound from the fridge, then it closes the doors. And this is another direction. And once we have a task-related knowledge, the next challenge is how we can teach the robot about new knowledges. So here, the student try to move around the robot in the laboratories by pulling the robot's hand. And she teaches that, okay, this is Professor Okada's room. So this is a fridge, and this is where the stair is. And by doing that, robot increases the knowledge in his database. And after that, she can say that robot, okay, please go to the fridge or something. Then robot guide her to the fridge locations. And this means that robot can learn the location, connection between the locations and the symbols. And if robot has such a capabilities, we can connect our system to not only the voice recognition part, but also the chat systems like this. So here, students type in the Google chat, like go to the message board, and we have a database or knowledge that message board is in front of the elevators or something like that. And robot go to there and take picture about what's some information on the message board. So I think this is some of the recent work in the undergrad student in my laboratories. And it is very interesting that recent students are very interested in communicating with robot in verbal communications. And because maybe our system is really matured, I can say. And system can take some input, like go to there and do some tasks or something like that. So people want to communicate with robot in voice messages and command the robot to do some tasks. So, and this is very, maybe I should talk too much, but this is very interesting because two robots communicate in human languages. And the interesting part of this system is that people around the robot can understand that what robot is talking each other because they speak in human languages. And here, robot try to grab the garbage, and human behind the robot look at that, and because human is currently much smarter than robot, and human understands that passing the garbage from one robot to the other is not succeed. So human says, okay, you have to wait, and fix the actions, and robot continues working. So this is what we are doing in our laboratories. So I think so far we are very interested in building the robots in everyday life. So left images is some result of our student. And for example, Dr. Furuta is doctor student in our laboratory, and he visited Bremen a few months and improved his PhD thesis. And here is we connecting our task-related system with classic AI planning system. And once we ask the robot to clean up table, then robot create this kind of the initial state and goal state, and pick the cup to the dishwasher or pick the bowl to the kitchen or something. And the left bottom part shows some recent trial for us to making the curry from the scratch. So robot have to cut the onions and the carrot and put the meat and do something. It is very complicated tasks, and we still interested in this type of the robot in daily environment. But at the same time, some students start interested in the everyday life with robot. So you can see some video in the left. Top left, one postdoc interested in the human-robot communications scenarios. But what she is interesting is not just robot and human communications, but using the robot to enrich the interaction between the children. So the target of the robot, the purpose of the robot is to enrich the human communications. So this is some example in the National Museum, and these children is not knowing each other before the robot is coming, but the reason of due to the existence of the robot, that they start talking or something. And this is our project to building the guide dog here. And the guide dog is different from the autonomous navigation robot, because for the autonomous navigation robot, the human around the robot is just an obstacle. But for the guide robot, human or owner needs to be protected by the robot. So robot understands the environment, and the robot's purpose is not to move from one direction to other by avoiding obstacles, but robot need to tell the owner about the potential of the risk, like car is approaching, or there is a stair in front of you, or something like that. So I think this is big difference between the research in left directions, robot in everyday life environment, but there is no humans, but also we are interested in the robot in everyday life environment with humans. So I think one direction we are interested in is how robot can keep learning from observations. And learning from observation is, I think, one of the classic research topics in these areas. But usually, we are interested in how robot can learn from humans. But we are more interested in how robot can keep learning from humans. Because we have a robot in our laboratory, and robot is doing some task every day, like picking garbage and bring to the base floor or something. But robot did not, improve its actions. So we want to teach robot about, okay, next time you have to do this thing or that thing. Or if human around the robot find some failure of the robot, we want to teach robot about, okay, you have to modify your actions like this in next time or something. So here, this is our trial to first, this student teach the relation between a symbol and location, like here is in front of kitchen, or this is in front of a fridge or something. And next, he teach about the relation between the symbol versus object. And then he teach about the symbol versus actions. And finally, for example, if user asks the robot about pour tea from the plastic bottle into Yanukura's cup. Yanukura is a surname in Japan. And he look for the database, which is taught by humans. And if there is no data inside, robot asks the users about, okay, what does a Yanukura mean, or what is a plastic bottle mean, or something. And this system try to continuously growing during by observations. And this is how robot learns each actions. And I think this is too detailed, but we want to fill gap between the verbal communication, like pick an object, and the robot, execution instances or commands. So first, okay. So first, robot observes the human's actions, and it segmented by the speed of the trajectory. And after that, we apply the input image to the video captioning modules, and it can output this is the unknown motions, this is open microwave oven motions, or this is pick a cup motions. And we use only the named sequences, and we observe the sequence of the human actions into the description of each actions, like open and pick and close. And after that, robot learn these actions, and then we can ask robot about like open the micro open commands. And this is some example, and I'm very sorry that this is all Japanese, but so he said, go to microwave, grab handle, open door, and blah, 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 blah. So robot can understand all of the actions. And then robot go to the microwave, open it, and go to the kitchen and pick the fried chicken and put in the microwave or something. And the interesting part is here. So you can tell the robot, like, when it beeps, grab the handle. It means a robot in everyday life, and a robot with everyday life. And this is some experiment conducted in this summer. And we are trying to understand the effectiveness of the robot with memories. And here we had some science talk in the National Museum in Tokyo. And this is open to the public, and especially for the children and their parents about interesting in the science and technologies. And she is one postdoc in our laboratory and explain about what is the robotics and what the robotics researcher is doing. So her talk consists of 14 episodes, and in one episode she talked about how did I start my research or something. And we have conducted about 10 talks, 10 times in some period about this talk event. And half of them, we designed such science talk in the without memory, which we call condition 1. And the half of them, we designed the talk in the with memories. Okay. And we use the same slide. And how did I start my research? And when she's a child, she's not good at talking to people, and robot can be, good friend for her. And in first condition, without memory, robot and researcher do some conversation in very casual manners. So robot asks, how did you start this research? And researcher says, oh, it was inspired by my own problem as a child or something like that. And robot just say, I see. And robot, in the condition 2, with memory, we write a scenario like assuming the robot know when she started the research. So robot say, your problem is the reason why you start this research, isn't it? And researcher respond to it like, you remember me, and I thought the robot would be able to come along among us or something. And robot will say, yes, that's right. So we had 2 different conditions, and we want to know how people or how children react with this kind of presentations. So I think it's very difficult to evaluate this type of the researches because this is National Museum, and they want people come to here to understand science and technologies. And if we ask that, okay, we are doing the research on this type of things, and here today's talk or this talk is about robot with memory or this robot without memory. And did you have some impression on robot with memory or something? Maybe, especially Japanese audience is very kind, and they tend to mark, it's a very nice, I was very impressed in the ankette. So here, we make some booklet, and we ask the children to write down or mark something during or after the talk. And here, we ask the participant, and please mark like button on the heart like this. So this is a 14 episode, like in the talk. And if a participant like or impressed the talk, each episode, they mark to the heart mark. And here, it is very interesting that the green part, 2, 3, 9, 10, 12, 14, is the episode that we we changed the contents between the 2 conditions. And the other one is we use the same talk in all events. And you can see there is some significant difference between the talk in the without memory and with memory. In talk 2, why she started the research, and the talk 14, episode 14, like this. So I think this is, we still under the investigation or evaluate the result, but we see some results that like this one so far. And another interesting method that we are interested to measure how people impressed about the interaction or presence of the robot is to ask the participant to write a picture diary. And I don't know if this is common in Europe or other country, but in Japan, usually young students or young children need to write this kind of things in the summer vacations. So we have a homework in summer vacations, and they write like, I go to park or mountain with my parents or something, and write the pictures. So this shows how people impressed during the talks. And here you see that robot and person is holding hands. And actually, during the event, robot and presenter is standing and with some distance. So there's no actual scene of this kind of interactions. But in the memories, robot said, the robot holding hand and walk to the laboratories. And it was very nice memory for robot like this. So we can say that such kind of the memories that robot talk in front of the people impress some of the students like this. So here is some of our preliminary research that conducted in our laboratory. So this robot, we built some functions that robot can remember when and where. And she's how can I say, guiding robot to her office to the presentation room every week. And robot memorize a picture of the locations. And robot sometimes say, did I been here before or something? And robot say, okay, we are approaching the big room because robot have been big room before, the lecture room before. And finally, when the robot arrived to the big room, it says, robot says, we come here last week, didn't we, or something. So this is some very simple example of robot have memory and using that memory to talk to the people around that. And I think this sometimes impresses people around the robot because she or he feel like robot is remembering this person and this some particular event that had together before us. And in that context, I think recent advance of the large-scale language model helps a lot. So here are some examples that we are using the clip to recognize if the butter in the pan is melted or not. So I think it's very difficult to understand or categorize or recognize this kind of phenomena in just a computer vision so far. But thanks to the language models, it can output that like this is solid butter or liquid butter from the images, and we use that information to distinguish the current situation of the butters. And this is another example like butter, boiled water, or onions. And this is interesting because when robot sees some images or input, robot can tell the human about what is happening in natural languages. And this is another example of using the large-scale language models. And in our laboratory, our robot has the daily patrol tasks. So robot, at 9 a.m., robot always wake up and walk around the laboratory and take some pictures. And here is some example about understanding what's happening in the laboratory. And we build the sequence of the questions. And the language model answer to that based on the images, like is there object in the table or is there a person in table or something. And by building some vectors, based on the answers of the language models, then we can measure the difference between normal situation and each days. And this can tell that day B and day D is very different, or day C also, different from day 1. And the router is not clean. And but it is not just robot understands the robot is not clean, but why robot decided it is not clean. So because of there is object or there is some person here or something like that. So I think recent technology can connecting the data set that was taken by the robot to the natural languages. So this is a conclusion, and we are interested in, of course, robots in everyday life, but also we are interested in everyday life with a robot. And I think the important key for the robot in the everyday life is remembering daily activities. And in order to do, by using that, robot need to continuously learning the new skill or new actions or new knowledges. And also, robot can share the memories, what people and robot do together. And I think the challenges here is semantic and linguistic understanding of task and memories, and social robot with knowledge and memory for complex tasks will be next challenge. I think this is big challenge for us. So you can see these videos because we have very nice quad-wrapped platform. We can put the robot, bring the robot out of the laboratory and move around not only the campus, but go to some park. I think it's 2 or 3 kilometers from campus. And if we bring robot to such a public space, especially children or even dog really like to communicate to the robot. And this is not so, how can I say, technically difficult things, but it impresses a lot. So we want to combine this kind of functions or features with the video that I show in the first slide, that robot doing some householding task or something. And we want to robot, okay, how can I say, for example, you didn't eat this vegetable every day, or you eat too much potato or something like that. So we need to start conversation based on the tasks or actions shared together. So this is what I'm thinking right now. And of course, most of the part is very mature, and I think we are looking forward to some new knowledge from our community in this field. So thank you very much.
Then continue with the program. Thanks a lot for a very cool talk. And as I promised, I think we saw a lot of robots doing very impressive things in everyday settings. And I think that's kind of what the lab stands for, right? And thanks a lot for that presentation. So our next speaker will be Ram Ramamurthy from the Edinburgh Robotics Center. And Ram is kind of in the executive board of the Robotics Center, and he has done very, very cool work in decision making in AI and bringing it to robotics, also using PR2 robot, and he has brought the decision-making competences of such autonomous systems into autonomous vehicles. So he was, his vice president of a kind of company, 5AI, right? And I think now he's also kind of in the UK research environment, also taking responsibility for one of the big projects, taking very important topic, trustworthy AI, and I think we all know how important that gets. And I think it's we are looking forward to your talk, and thanks a lot for being here. And yeah, and I think Edinburgh I think is one of the coolest places in AI. So I was there. It was the first university I was outside of Germany, right? And it was at a time where actually Edinburgh and the people working in knowledge representation and reasoning in Edinburgh, they were fighting against MIT, against CMU, and Stanford, and wrote papers like In Defense of Logic, so that was kind of what I was brought up with at university, and it was a very enjoyable time. And I think thanks a lot for being here.
Well, so firstly, thank you for having me. It's my great pleasure to be part of such an exciting program. I've enjoyed the talk so far, and I hope the next one doesn't disappoint. So as Michael mentioned, I'm part of Center for Robotics, and this represents a very wide spectrum of co-investigators that I have the pleasure of working with, all the way from low-level hardware, up to cognition, programming languages, social issues. But of course, I mean, a half-an-hour talk has to have some structure, so I'm going to focus attention on the outcomes of one particular project that I've been working on for a few years now. And although it pertains to activities that happen every day, they're going to be slightly different from everyday activities in the sense of what happens in your home. And I'll say more about that as we go along. So firstly, a lot of what we are interested in when we talk about everyday activities is that the robot must coexist, interact, or do something with a human co-worker. It could be the human's boss, it could be teammate, it could be student-teacher relationship, whatever. So here are some examples of the kind of robots that we've built in our lab. They're different projects, but they all have this underpinning idea that the robot is working together with the human. On the top, what you see is that the human does something, we understand what they're trying to do, and then the robot has learned from that experience. In one of the bottom videos, the robot is actively doing intention recognition and trying to coordinate with the human such that it's doing an assistive task. So for me, it has the analogy has always been, imagine you're a car mechanic and you want somebody to fetch you tools. And then there's yet another one you see at the bottom, where we are really trying to understand human skill in a multimodal way, all the way from cognition, down to what's happening in terms of forces and so on. So the project from which I'm drawing many of the results today, it was done in collaboration with a team of medical practitioners. Paul Brennan, he's in charge of the neurosurgery practice for Scotland. So he's, of course, an expert in many ways, but the tasks we were looking at were quite far from neurosurgery. And much of what I'm telling you, if you look past the fact that we originally had a medical motivation, are things that could be happening in your kitchen. So surgery is not that far from food preparation, depending on your point of view. So, but the scientific ideas I'm trying to get across to you have to do with this idea of how can we take learning from demonstration, which is a long-standing theme in robotics, all the way to an actual discussion in the way that a teacher-student relationship actually works over an extended period of time, where concepts are discussed, concepts are formed, exchanged, coordination is achieved, and all of that. So I'm going to show you glimpses of results from various bits of projects, which start from the idea that we want to have experts give us some understanding. We want to ask the question, how do we then understand the representations that the expert has given us? Then we want to get to an important element that is increasingly a big part of my work, which is safety. So like you and like all of us, we've spent quite a few years by now creating robot demos. We've all done this. But we all know how delicate those robot demos are. I mean, I say from my own personal experience, every time a distinguished visitor comes, we herd our graduate students to very carefully set up the lab. But we need to go to a point when we are well beyond that. We need to go to the point that when we have assurance, we have the idea of a product that will reliably work. So what will it take to take those steps? Okay. So let me then begin. I'm going to begin, now there are going to be many technical details I'll gloss over here. I'm very happy to talk to you about them at leisure, but let me kind of briskly take you through, a few different pieces so that you get an idea of this full pipeline. Let me start with what is, for my collaborators, a very simple control tasks. If you're in any kind of surgery at all, the simplest thing you do is to excise something. Excise meaning cut it out and take out a lesion. Imagine something on your skin and somebody has to take it out, right? From a roboticist point of view, you start and say, this is not that hard. I mean, yes, the context seems a bit odd, but then it's not that difficult. It's actually just a planning problem. I have a geometry. I want to move my knife around it. But all of us who've thought about this problem deeply would realize that you don't want to do it in the classical planning way. You want to acknowledge that there's actually a little bit more than just the geometry around which you're moving your knife. There's perceptual uncertainty. There's the need for closed loop control so that you can accommodate what's going on. And so the most important thing that we were interested in was to say, okay, how do you bring in the low level with the high level? By the low level here, I mean, what does it feel like? And so here you see an example, a very kind of stylized example of a knife going through tissue of, phantom tissue of different consistency. And you can very clearly see that there's a signature in the force channel, right? And this signature is very useful because if you make use of the signature along with the geometry, if you make use of how it feels to your forces, along with what it looks like to my vision, then you can come up with a controller that actually collapses the complexity of the original problem. I had geometry with uncertainty and so on. Now I've changed it to no, it is what it feels like, and it's essentially gliding along a particular surface. And I'm actually able to do a much better job of this excision task. And it has to do with using multiple modalities. And a lot of human expertise lives in the way that we join these multiple modalities. We have knowledge models in our head that simultaneously talk about, the logical idea of what the object is, all the way down to what did it feel like to my muscles, right? But then I've shown you an example in a simulation environment, and the obvious question you should ask yourself is, does this actually work? Is there anything I'm missing when I go to the real world? So here's my canonical lab task for this. Many of you might have done this at breakfast. I want to take a knife and I want to scoop out a piece of fruit. There are significant uncertainties here. I don't know the geometry of the pulp versus peel in interface. I don't know the material properties. But I'm going to argue and I'm going to show you that actually, if you think in this multimodal way, the controller is remarkably simple. All there is here is two mediums, mu1, mu2, as far as you're concerned. And there's a boundary between them. And the template controller is very simple. You glide along in such a way that you're exactly at a halfway classification point between the soft tissue and the hard tissue. If you can move your knife around and you can feel it, which you do effortlessly, then that's your controller, right? And you have to do a little bit more. You have to do a very good job of this classification, and I won't go into the details of how you do it. But if you use that classification loss as the error function to a controller, all this is a PD controller. So the complexity is remarkably low, provided you use the right channel and provided you use the right kind of description. And I'm going to say that much of human skill, if you look just right, is going to be like this. So here's one example I've given you. But actually, this example is by no means a carefully chosen kind of special case. I'm going to argue that actually much of life is exactly like this. And those of us who find ourselves in debates about, neural versus symbolic or high level versus low level, we constantly keep having this discussion, whereas my perspective is, no, you just want to find good ways to combine them. At a certain level, expertise is a programmatically described, knowledge-heavy kind of enterprise. At a different level, expertise has to do with, how do you take very rich sensory signals that you have the privilege of because you have a body, and somehow you want to combine them. And we've been looking at many, many architectures in which we can do this kind of combination. And here are some examples that I'm showing you. So I started with grapefruits from your breakfast, and we are actually, taking that all the way to surgery. Here are some examples of data that we are collecting from surgical trainees, and they've been given exactly the task I started with. We want to understand what all goes into their skill in terms of how they actually perform a delicate operation. We created a special kind of instrumented scalpel, so we get forces all the way from inside as well as we get data from the outside. I won't bore you with the process model, except to say that there actually is very interesting, rich structure, not just in the forces that they experience, but how do they move their fingers, when do they tighten and loosen. So you can easily imagine what you would do in terms of, put your finger on the tissue, move it around, and so on. So there's actually a very, very rich program. But that program is written in the language of low-level forces, low-level perception, and low-level control, right? And so by studying this in this level of detail, we are extracting all sorts of information, such as the distinction between a really good expert and a novice is in the subtlety of exactly when they decide that they should tension something on one. The other hand is the trivial PD controller I showed you earlier on. And if they begin to lose that simplicity, they do something else with this hand such that they go back to the simplicity. So it's a very, very delicate program, complex in a certain way to maintain the simplicity such that they can get the rest done. And we are looking at the same kind of thing in a different domain where we've been trying to understand what is the skill that a physician has when they're trying to use ultrasound units to scan. At least the women in this room might be familiar with the ultrasound scanner from maternity wards, but actually it's a very common instrument used all over medicine. And what we're interested in is how do people actually combine their feature understanding of this is that, and this is what the structure looks like. And can we understand when they modulate the forces, move the scanner around such that they actually locate those features? It's very hard to do this as, image processing first, geometry next, and control later, just as I said in one of my earlier slides. So we're looking at ways in which this is an integrated architecture. And the reason we're doing all of that is so that one day we can have a robotic ultrasound scanner like what you see here, which has been unleashed to do the job by itself. Right now, it's only scanning a phantom, which has a kind of fake lesion inside it. But we are trying to work with people, such as in fetal medicine, so that we can go further and further towards trying to understand what is the skill that a doctor has that allows them to diagnose all the important conditions very early in life. And another advantage of trying to automate like this is so that we can address global health issues where there's a scarcity of expertise and so on. So this is a whirlwind tour through a number of different control topics that appear in sensory motor skill. Now, in the remaining time that I have, I want to open the box a little bit and talk about a few issues that have come up for us. The first issue is we want experts to talk to robots in an extended conversation, which means we want the robot and the human to exchange information, not just in terms of a few class labels, which we can easily do, but actually we want the human to be able to make corrective actions and suggestive actions. It's the equivalent of if you were teaching me to drive and I start driving, you might say, no, slow down. If this happens, don't do this. Do this more gently or don't do that. Oh, these kind of conditions are these specific kind of maneuvers. So actually, the way we use the language spans the spectrum from concept labels to kind of modifiers and corrections and so on. And we want to ask, how does this compositional semantics actually get grounded also in the actual action? So I don't want to just take a label and invoke an action. I want to be able to modify the action and so on. So we've been coming up with a setup like this, which involves data collection at all of those levels. So we get teleoperation data for the low level, we get dialogue data for the high level. Occasionally, we get things like eye tracking data. And the point is to try to put them all together. So we are using emerging neural network architectures. I will not dwell on the details of these machine learning models. I'm very happy to discuss them if anybody's interested. For those of you who are not using them already, all you really need to understand is that the way we are using these architectures is to exploit the structure in the latent space. So this particular model is called a variational autoencoder. And the key idea of a variational autoencoder is that there is a latent space into which all of the high dimensional data is projected. And we are trying to explicitly structure this latent space such that the semantic concepts we are interested in get embedded into that latent space. So for this particular model, we've modified the usual training process such that we've added an additional term for classification. And the classification loss is going to refer to the fact that, as you see in that two-axis diagram, we are going to force the latent space to have the structure that this axis represents shape, this axis represents color, and then in higher dimensional versions of the same thing, we are going to put in forces and other ideas like that, right? So what this allows us to do is to create an architecture that creates the symbol onto which the rest of language is going to ground. And so we've created a whole collection of these kinds of networks that start from object properties, things like shape and color that I showed you, relational properties such as on top of what is next to what is to the left of what, and also connections with things like forces so that I can say do it more gently, drive faster, right? And the way in which we put them together is that first we train with respect to, once we have the object properties, we train with respect to relational properties by having data like that. Then we sequence them together and we chain them, so such as this is now jumping on top of that, this is now going towards this. And if you put all of that together, and I've clearly gone very, very fast, but hopefully this gives you an idea. If you put all of that together, then what we are trying to do is to go from demonstrations of a multimodal kind that people have been giving us in a corrective dialogue, in an extended corrective dialogue with the person, such that we can then tell the robot to do things like this. So here's our PR2 robot in the lab. It has been given reasonably complex instructions, place this on this and so on. But it is able to do this in a compositional way. So the whole sentence is not a single label. The whole sentence is actually composing from primitives that it's flexibly kind of marshalling at runtime. And not only that, we can include in that dialogue concepts such as, now do this faster. I taught you how to do this, now flip this to the left and do it like that, in the same way that I would teach a novice how to acquire new skills. So this is one piece of how we do this. And this piece for me is important because I think that in order for us to have reliability and safety and kind of competence in a broad way, you have to be able to interact with your robot long enough that it actually learns. This is how I train a human expert. But then taking this idea of safety even more seriously, I want to now make a connection back to in defense of logic, as Michael said. I mean, if you're an actual engineer building a real product that's going to be deployed on the streets, you don't hope. You don't just train a robot and say, I think it'll work. You actually want to be able to give a specification. You want to go to a regulator and say, I have tested for the specification. So how are you going to do that? And the crucial piece, as far as I'm concerned, is how do you take existing learning methods, such as for learning from demonstration, and combine it with additional annotations on top, which are logical specifications. They could come from natural language dialogue, but they could just be logic, for instance. In this case, it's a linear temporal logic statement. And I want to ask, how do you then modify your training pipeline such that you can incorporate statements such as an LTL? So the underpinning logic is, in this instance, a dynamic movement primitive. This is one particular way in which people do learning from demonstration. The details of this are not so pertinent, except that it's a particular parameterization of a controller that lends itself well to imitation learning. What is important for me is how do you take something like this, which is a well-defined optimization-based learning procedure, and combine it with what is a seemingly incompatible logical statement, such as an LTL, right? And LTL, for those of you who haven't had much familiarity with it, is really a branch of logic in which you want to be able to make statements about the dynamic evolution of some kind of a system. And what we are particularly interested in is statements such as until this happens, or always such a condition is true. This is how you talk about things like safety. What we actually do in the machine learning is that we combine in the same way that neural networks are trained or kind of various control architectures are trained. We combine what is normally done in terms of a loss function for a controller with an element in which the logic has been compiled into a loss function, and then we are trying to use an adversarial training pipeline the details of which I can go into later, or you can look into the paper for, which allows us to now jointly train both the logical statement and the underpinning controller. And what it allows us to do is to do things like this. We've shown this robot a demonstration of how to pour from a cup, but then we want to make a correction. We want to go back to it and say, no, 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 you don't tilt your hand until you're directly on top of the cup. And that bit has been said to it in logic. And so what the robot does is kind of seamlessly combine both kinds of instructions. Here's another example in which we've given it a specification such as you always do this, and then you do this, or you always have to kind of respect this. So these are all steps towards building a safe robot, but doing it in a human-centered kind of dialogical fashion. I want to end with one last section. So I said at the beginning that safety is an important ingredient of how we are doing things with controllers. And along the way, I've introduced the idea of speaking to humans, using high-level representation such as logic, and incorporating all that into machine learning. One natural outcome of all of this is that we can now bring to bear on this everything that software engineers and other forms of engineers have known for a long time, such as state-of-the-art testing methodologies, state-of-the-art verification methodologies. So one of the things we are now looking at is, can we take various ways in which you can do testing for edge cases and apply that because you have logical specifications as part of what you've learned from the human. And so the way in which we go about it is that we turn finding edge cases as an experiment design problem, which we can solve in the same way that Bayesian optimization or various kinds of search strategies are addressed by people. And then the optimization here is to try to break the specification. If I know that this is the underpinning spec, I look for the simplest example that actually breaks that spec. And then I conduct experiments by tuning the world. This is the equivalent of me changing the lighting on the external world such that I begin to get your braking system not to do what I want, right? And so this is a well-defined sort of problem that is used in a number of different safety engineering methodologies that we can now bring into robotics quite easily. The key idea here is that you can take the logical spec, and there is a notion of satisfaction of this spec and a distance from satisfaction, which you can turn into the metric that you're searching for. That's the core scientific idea of what we are trying to do here. And because we have that kind of a representation, it lends itself to thinking in this way. And so we've done a number of experiments with manipulation robots. For instance, here the manipulation robot has a logical spec. And we know that what we want to look for is, how much do I have to change? How much do I have to change friction? How much do I have to change the mass such that the controller starts to break? And then that tells me, go back and train there, or tell me what's wrong in that region, and so on and so forth. So I'll conclude before I give you my actual scientific conclusions, by mentioning this large program that Michael talked about at the beginning. I'm part of a UK-wide program on trustworthy autonomous systems, which is part of the UK government's recognition that AI is now finally beginning to work such that normal people should be worried, which means us scientists should start to address that worry. And so this is a fairly large investment across universities, across disciplines, and I lead one of the nodes within this program. And in my own node, this is for the first time in my life that I'm really stretching across disciplines. My co-investigators range all the way from legal and social scholars and data ethics people to AI testing, natural language processing. So it's a very diverse project. But the ultimate goal is something we all recognize, which is, what would it take for us to achieve a degree of safety in an AI-based autonomous system such that we would actually be happy for it to be among us in this room without being tended, right? So to kind of conclude my talk and give you my scientific conclusions, I'm really excited by the idea of autonomy in an assistive capacity. I've given you assistance in the context of medicine, but it's exactly the same thing in your home or your kitchen. And two ideas that I'm particularly excited by and that are featuring quite a bit in my current work, I'm interested in the idea of machine teaching or extended dialogue with a robot. I'm also interested in the idea of taking safety seriously at the representational level and trying to figure out ways in which we can do that. And this is manifesting itself as a number of specific projects. We're trying to understand human skill from surgeons. We're trying to look at the combination of logical and dynamical representations, which in AI as a whole, people are thinking about as neurosymbolic AI. We're also interested in taking multiple modalities, all the way from forces, up to kind of logical, visual things that are coming out of language models and so on. And taken together, we hope that we will build more and more capable robots that will blend into our lives such that we start to ignore them more. With that, I will thank you for giving me this opportunity to speak to you, and I look forward to the discussion later.
So thanks a lot, Ram, and very cool talk. Yeah, so we have the discussion for later, and I think now it's kind of the next speaker. Is it break first?
We have a coffee break.
Oh, first, okay. Then we have a coffee break first.
20 minutes and the exhibitions are open now.
Yes, oh yes. So that's what I wanted to announce is that we have all the labs open, so you're welcome to go into the labs at any time, look at the things we are doing, and have a good time. And so yeah, we are showing what we have here. So have fun. session, right? So yeah, thanks Benjamin for being here. So Benjamin is actually a doctoral student here, but he is actually working at a company. It's Artimines, and they are doing robot planning and robot control. And I like Benjamin's work a lot, and for several reasons. So for one, it's actually bridging the gap of some of the advanced techniques that we have. So it's knowledge representation and also plan-based control, and bringing that in an industrial control system and doing manipulation tasks with that, right? And it also shows that if we are working on cognitive robots or something like that, it's not a monolithic thing that cannot be, but actually the parts can be used. And the other aspect of Benjamin's work I like a lot is that he's actually bridging between the two worlds of deep learning and knowledge representation and reasoning, and shows how the two worlds can actually work together, and also in a way that we are kind of close to having products in that area. So Benjamin, we are looking forward to your talk.
Thank you so much, Michael. I'm very happy to be here. I'd like to talk today about knowledge representation and reasoning in industrial robotics. I'm a research scientist at Artimines Robotics. We are a software company based in Karlsruhe, working on bringing artificial intelligence methods into industrial robotics and creating real commercial value from that. So when most people think about industrial robotics, they think about systems or production systems like this, right? Very advanced, very complex, with a lot of big, usually orange robots doing very fancy things, and think, hey, actually, don't we already have everything figured out, right? We can make these very complex factories with high degrees of automation, build cars and complex systems with industrial robots. Where are the challenges? Why do we need research in this? Well, it turns out that not every industrial process is right here in and beyond the 2020 stage Industry 5.0, where we have mass customization and highly, autonomous production facilities for everything. Rather, we have actually a majority of production processes that are still stuck sort of in the 2000s phase of what we now call Industry 4.0, and we are still, in many processes, are in the transition into Industry 4.0. So we're digitizing processes, we're integrating sensors, we're integrating cameras. We're very much building the data infrastructure on which to do machine learning and artificial intelligence, but we are not there yet for many processes. And in fact, there's this fat tail here to the left of several production areas that are still very much in the 20th century style of doing automation, which does not even include any sort of data. So now we're trying to, of course, move this distribution farther over to the right. And the fundamental question is how to do that. In order to address that question, we need to look at what are actually the barriers or the frontiers in industrial robotics that we need to overcome in order to be able to move this distribution to the right. So actually, it turns out that in industrial robotics, the frontiers are very much the following. We have subsymbolic optimization problems everywhere. So this means we have to deal with process noise and optimize that way. We need to deal with wear and tear, manufacturing tolerances at the small level. These are sort of not really planning problems per se, but rather optimization problems over continuous domains. In the video, you see some example applications where these kinds of problems are particularly important, where you deal with noise. In this case, also, you have, for example, imperfections on surfaces. You have deformable objects like cables, very small. We have to use sensors to compensate for deviations. You need force-controlled insertion. You need to do quality assurance in these sorts of domains. And you have this sort of, yes, you have structured environments, but at the same time, you still need to compensate subsymbolic, also very small scale issues everywhere. And you have so this is basically the standard view, but you also have more. So you have the problem that now most of these advanced processing stations with where the parts are being moved, sometimes the robots are being moved within the factory. So the thing is, though, not all is lost. We are also having some assets that we can deal with, such as partially structured environments. We have control over our environment, and we have structured task and domain knowledge that we can leverage. And so we are very much sort of trying to figure out how can we leverage these assets to address these problems. The core thesis, or one core thesis that I'd like to sort of present here, is that there is actually an AI adoption gap in industrial robot programming. So we haven't solved nearly as many of these problems as we wish we had. So despite the ubiquity of industrial robots within many industries, the uptake of AI in industry has actually been surprisingly slow. We call this the AI adoption gap. So AI adoption is very much limited to perception at this stage. You use CNNs, for example, for object detection or for quality assurance. But for highly complex programs such as these dealing with deformable objects or heterogeneous execution environments, I talked about this earlier, where you have many different parts, sensors, PLCs, robots working together, or for problems of real-world physical manipulation of objects where you deal with a low-level physics, or where you have human involvement, there AI adoption has been extremely slow in industry, partially because industry practitioners are reluctant to adopt these strategies that they consider being high risk, right? So sure, you have powerful learning algorithms, at the same time you risk failure, and these are all areas in which failure can be very expensive. You also have these high trust requirements. It's also related to this. So when you have humans and robots interacting together here, for example, polishing a surface in a force-controlled way, you really don't want the robot to act up. You want the robot to act always in a predictable way and in a completely safe way for humans. And guaranteeing this with sort of state-of-the-art machine learning algorithms is quite challenging. And this is where we as a company come in and try to solve some of these challenges. So Artimines, first and foremost, was started as a pure software company. We started building software to enable industrial roboticists flexibly and quickly create complex robot programs without needing sort of low-level programming knowledge. So a high-level user interface-based, sort of the visual studio for industrial robotics, one can say. But then we started also becoming an automation company because we saw, hey, this isn't actually enough. We also need to offer services to enable our customers to effectively use our software. And we also now have a department where we sort of help our customers along the way of getting software deployed into production. And now we're also, in the past few years, have started to become an AI company and started to see, hey, we actually need to use machine learning and knowledge representation and reasoning, it turns out, to address some of the problems that just regular programming paradigms can't address. And we offer two products for this. Robot Programming Suite to the left is basically the Visual Studio or the desktop's software for industrial robot programming, which has a drag and drop interface where you can sort of build your robot program easily, and a simulation environment, and we can create code for all kinds of robot platforms and basically also have an execution environment. And to the right, our data sort of platform, learning and analytics for robots, which is sort of this web-based application that collects the data and allows users to analyze it, create dashboards, and also optimize the production process afterwards. And our core intuition is that everything really depends on the program representation. So our program representation, we call it Artimines Robot Task Model. It comes from the concept of task graphs, and it is a directed graph of parameterizable, what we call motion templates. You see these things in red, that you can easily drag and drop into your program, create programs on the fly without needing to know how to actually write robot code. And these are robot independent, so these are generalized skills, and you can combine them to make very complex programs. We have motion skills, perception skills, basic control flow operations. You can do logic, elementary math, etc. And these templates basically parameterize motion planners underneath, and you can create low-level robot motions from that, and force controllers and so on. And the fundamental insight that we had is we need to compile everything into native robot code. We don't do real-time execution, the ROS style. The reason for this is that in industry it's very important to have your programs be certifiable and comply to industry standards, such as the Volkswagen standard and so on. And this is very hard to do with ROS or ROS industrial style real-time control, and that's why we choose the compilation path and have different compiler backends for different robot platforms that then generate robot code. So our core insight here is that task-based robot programming is really key to solve complex automation challenges. So fair enough, but how does that solve us? How does that help us with a more complex challenge that I've talked about earlier? And here are our ideas to actually bridge the AI adoption gap based on this flexible robot program representation that we have. The first is that we systematically leverage the properties of symbolic composition, so modularity and abstraction that this symbolic program representation offers. And it has two advantages. It is intelligible, so humans can easily understand it, as opposed to sub-symbolic black box neural networks. And it is fundamentally interoperable, so you can swap out parts of your program, or you can transfer programs between robots very easily. Then we also want to leverage structured knowledge representations. So we want to reuse human domain expertise, reuse existing planners, and generalize through reasoning. And I will show you in a second in the next part of the talk how we do that. And the last part of the talk will focus on neurosymbolic programming. So how can we actually combine sub-symbolic neural networks with this program representation to actually enable the data-driven optimization of program parameters? So if we look at how industrial robots are programmed in the wild, we see that this is done performing 4 steps. We have programming, commissioning, so actually combining software and hardware together in the robot cell, ramp up, which basically means that you slowly increase the production, you reduce the cycle times, make production quicker to actually in the end achieve your final sort of operative speed, and then operation, which is focused on maintenance and reconfiguration. And you have all of these opportunities for AI assistance here in blue. And let's focus first on the program synthesis or program refinement part at the very first step, the programming step. And this is where we use knowledge representation and reasoning for the particular subproblem of program synthesis. How can we bootstrap robot programs using knowledge representation and reasoning? Taking the example task of surface finishing, you see that here on the left, 2 videos, for example, one grinding a metal surface and the other is deburring an engine block. And so when we thought about this problem, we thought, okay, let's make an ontology of the domain. And it actually turns out this is quite suitable for this, as most industrial domains are. You can decompose them into subdomains and subtasks. And for example, you have abrasive or adhesive surface treatment processes. And for example, sanding uses different tools. In this case, I've shown 2 belt and disc sanders and so on. You have different processes for each, how to use them. And so this looks already very much like an ontology. The intuition is we can use this kind of knowledge, and we know how to do all of this if we can only represent it properly. And as an application use case, we considered the refabrication of wind turbines, which are right now not really recyclable. So these are actually end up in landfills, which is very wasteful. We want to change this, so our idea is to refabricate them. That's a very manual process. Why is that? Because you have composite materials. So basically every or many wind turbines blade types are different. They're built differently, they have different components, and it requires a lot of manual reconfiguration and manual expertise to actually program your robot for this particular blade. Also, they age differently depending on what birds flew into them over their 7-year time of operation, or what kind of wind and sun conditions were there and so on. They age very differently. So our idea was to actually first model the process. Process is very simple. First, we use a sensor to classify the surface, basically scan the surface. Then we select the right tool to finish it, polishing, grinding, maybe sanding it. We do path planning to get our tool path. We actually perform the sanding. Maybe if there's an error, we have to do some error handling and so on. And it turns out that for at least the tool selection and path planning part, we were able to already use NoRob as a knowledge representation and reasoning engine for this. And we're doing this in the RoboGrind research project together with our partners that's going on right now. So this is what part of our ontology looks like. Here, for example, I show the material part of our ontology where we have modeled several different materials such as aluminum or wood or glass. You find all kinds of things in these blades. And this is the process model that we also turned into an ontology. And you see already it looks structurally similar to the plan you saw before. And we used primitives from the Soma ontology to model this, which actually has a very nice way to model these kinds of workflows. And then we built, right now it's a little command line interface tool, which basically is a KRNR expert system. So it asks you, for example, what type of blade do you want to grind? We say blade 3, it tells you what grinder to use. And then it parameterizes automatically a robot program that has the right robot with the right tool, etc. It instantiates the environment, and then it asks you, okay, how much do you want to remove? And you say, okay, 12 millimeters. And it computes the right robot speed for this grinder, this amount of material to remove with this material. And we have human demonstrations in VR. We see this on the left, where a human is taking an object and putting it into a shopping basket, or the inverse we also consider. And the goal is to do the thing on the right, where the robot hopefully autonomously performs the same task in the real world. And this is our approach to doing this. Now, I won't go into all the details, but you see that the VR demonstration here is what I call action interpretation. So we derive a set of abstract tasks from this human demonstration, from the set of actions. So we move from the event level to the task level. That's an interpretation in a way, trying to see what did the human actually want to do semantically. And we use NoRob for this. We generate a task sequence, which basically relates also objects to tasks. We know that for example, the picked up object in this task was this, for example, the healing salve, or the target object for the placing task was the shopping basket. And then at the task execution part, we take this, what we then call underspecified plan, and specialize it, or specify the missing parts, infer the missing parts from our real-world environment and actually execute it in the real world or generate robot code for it. And the whole thing is based on the CRAM cognitive architecture, which we use for this. This is an example of the knowledge that we use as an input. This is the segmented timeline from the human demonstration. You see it already contains a lot of semantic information. The orange part, so the blue part is what we actually get from the VR engine. The states, such as, for example, that two things are in contact with each other. And the orange part is the sort of sequence of anonymous actions. At this point, we don't know what these actions mean yet. We just know there must have been some action because the configuration of our world changed. So between this and this, there was some change. We don't know exactly why, but some set of things in the world changed, so there must have been an action. And we segment it that way. And we use sort of situation abstractions to model what changed exactly semantically. And then we have a specification of tasks. So we can, using NoRob, it's very easy and very succinct to specify tasks. And the process of mapping, so this interpretation problem of mapping an action to a task, can be specified in 5 lines of code, which is actually quite neat, using these kinds of knowledge representation and reasoning techniques. And you can say an action corresponds to a task if it satisfies pre, runtime, and post conditions of that task. And then you can infer the parameters for that task given that. And you don't have to read all this code, I will explain it. So this is how you define a task. Also very easy, you can define picking up in maybe 12 lines of code. And you can say the preconditions of picking up is, for example, that an object was grasped. So picking up is basically if you have already grasped it and you undo the contact, so you take it away from a surface. The object is already grasped and it is supported by something else. So maybe this cup here is supported by this table. It doesn't have any runtime conditions. And as post conditions, we can say that at the end, the object is still grasped, but there is no situation at this point in time in which this object is supported by the table anymore. So we know that we have picked it up. It's very easy to specify these, and we have done this in Noro. And then we have a task sequence. So we're now at the task level. We know that this action corresponded to a picking up task. And we actually also know that we have two things that are involved in it, the shopping basket and the healing self. Healing self is picked up out of the shopping basket. And now we have to actually turn this abstract inference into real-world action again. And this involves filling out the blanks, because we don't know, well, we know that it was the shopping basket in VR, but we are not in VR anymore. So what is the equivalent of shopping basket in VR in the real world? We have to find that out. And for that, we use the Robo-Sherlock sort of perception system, which allows us to ground these abstract concepts in real-world things that we can detect. We can see, okay, this is my shopping basket in the real world, so there it is. I can place things in there, or I can pick up from there. And we generate code to do that. And you can see we can simulate this and actually also execute it in the real world. And the simulation looks very similar to the real-world execution. And it actually puts it onto the hanger. So this much for symbolic program synthesis, where we can actually do these kinds of very complex inference tasks quite simply using knowledge representation and reasoning. And now for the second part, which is neurosymbolic robot programming, which we want to use to solve these optimization problems that I was talking about earlier, dealing with noise, for example. And for this, we have augmented our program representation by what we call differentiable shadow programs. We have to bridge the gap between the neural world and the symbolic world, and we do this using this shadow program paradigm. So if you look at our symbolic program here, just consisting of two motions, what we do is we construct a parallel model, which is also a sequence, but a sequence of neural networks. Actually, to be precise, a sequence of differentiable program graphs, which actually have a differentiable motion planner inside, but also a deep residual GRU, so a neural network. And this is kept basically in sync with our robot program. It's a shadow program. It's a neural shadow. You also have this paradigm in explainable AI, for example, where they also use explainable shadows for neural networks. We do the inverse. We have neural shadows for a symbolic robot program. And this thing is end-to-end differentiable. A robot program, you can't differentiate through a robot program. You can, however, differentiate through a differentiable program graph. And you can also do forward propagation. We can predict the expected trajectory given our program parameters. And this also, of course, depends on what we've learned. So this depends on what we learned in our neural networks from data. And then we can backpropagate and optimize our program parameters. Now, the cool thing is we don't want to optimize the network weights here. We want to optimize the inputs of our symbolic robot program so that we can minimize some sort of loss over the real world, for example, cycle time, or maybe maximize the success probability of our robot programs. And this is a nifty way of doing this, because you can do things like optimize relative contact motions. We tested this in this PCB assembly domain. This is our very simple robot program. One task can't get simpler than this. Relative contact motion, we want to optimize two parameters, velocity and acceleration, in order to not bend the pins. So we don't want to hit the surface too hard. These are very fragile. At the same time, we want to be as fast as possible. And we want to be successful all the time. As a human, this is very hard to do. If you want to fine-tune a PID controller to do this, it takes trial and error, very expensive, takes a lot of time, and you overshoot very often. This is the data that we see. And now if you want to hit exactly 5 newtons, for example, for a human, very hard to do. After optimization, our robot program does it every time. And this was quite an impressive result we found. Here you see the video for this, but I'm going to skip over this. We also tried to have a look at search motions. Search motions are quite cool because search motions inherently have a trade-off. You trade off time for search, but the gains from search are increased robustness. So the question is, how much do you want to trade this off? How much time do you have versus how robust does your program have to be? You also have non-stationary noise processes, which is quite nasty because if you tune your search at maybe time point 0, and then you let your program run for hours and days and weeks, and then at time point 1000, you notice that your distributions have shifted, and suddenly your search is useless, even though you have tuned it before. This is very difficult. You want autonomous systems to be able to deal with these non-stationary processes on their own. And so our question was, can we actually find an optimizer for these search strategies that does all these things and is data efficient at the same time? It turns out that using neurosymbolic robot programming, we actually can, and we can transform, for example, a spike search where we probe the surface in a grid pattern, naive grid pattern here. You see it in red. Come on, maybe not. Okay, well, there was this red grid, and we want to transform it into an optimized pattern that actually fits the whole distribution over time. And here's how we do it. We take our robot program, we collect training data, and we train it actually first on simulated tasks. So a very large number, in this case maybe 1,000 tasks, because simulated data is cheap in simulated environments. And then what we do is we take one test task, collect 128 training examples. This is very cheap. Industrial robots run for much longer than that, so not really a problem. And then we fine-tune. We run the optimization procedure that I showed you earlier. We execute this, and that results in more data. So because in industrial robotics, we have this continuous loop of executing and again, we can actually do lifelong learning and retrain to actually keep the model updated with these non-stationary noise processes. And it turns out that this optimization procedure ticks all the boxes. It's heuristic-free, data-efficient, robust, and black box. So we can actually use this not only for our own robot program representation, the ARTM, but you can use this on CRAM plans or UR script, universal robots functions, or KUKA programming languages, and so on. And here's an example of two non-stationary noise processes, drift motion on the left and Brownian motion to the right. And you see that the spike pattern keeps up with some regularization, so we are actually lazy. You can see here, maybe we don't want to update all spikes with a distribution, but we actually have some spikes which always follow where the hole is likely to be. I would also like to point out that we have been, in the last 2 years, when we started working on this, building out an infrastructure for technology transfer and combining basic research with sort of more applied research at higher technology readiness levels, which we call our innovation lab, where my boss, who will be there tomorrow, Darko, he will join the panel and be there tomorrow also if you have questions for him. And myself and our very talented students are working on publicly funded research projects from all manner of domains, be it also robot-assisted laparoscopic surgery, programming in VR, service robotics, industrial robotics. You can check out our website where we have examples from our projects, and we are also partners in several regional sort of affiliations, but also we're loosely affiliated with EASE, and also then, of course, with EU-Robin, which is very exciting for us. I would like to conclude by reiterating the main point. We'd like to bridge the adoption gap in industrial robotics. And how do we want to do this? By using 3 sort of core points. A, structured program representations are key, and that enables the use of knowledge representation and reasoning in industrial robotics and allows us to be much more data efficient, much more energy efficient, explainable, and interoperable. We want to use structured knowledge representations, which we actually have in industrial robotics, reuse domain expertise, reuse existing infrastructure, and generalized reasoning. And we want to use neurosymbolic programming as a way to do data-driven optimization over these programs. I thank you very much, and I look forward to your questions.
Thanks a lot for your talk. Either there is kind of, because we didn't have discussion questions before, right? And if there's one question like for understanding, I think that's okay, but others we would take it offline. Yeah, so thanks a lot, Benjamin, and I think that's kind of cool work, and it's work that shows that the research in those areas can have impact in more near-term applications, right? And that it's important, and it's not necessary to think of these cognitive systems as one big thing that never comes, right? But we can already start to get pieces out, inject them into the control programs, and have an impact, right? And I think that's kind of very important for our field to develop in a healthy fashion, right? So, yes, oh, cool. So, yes, welcome, Giorgio, yeah, and yeah, so we reorganized a little bit, right? So Giorgio was stuck at the airport in Frankfurt, I believe, and we didn't thought that he will be here in time. So we reorganized the program a bit, and Daniel takes over. So and Daniel takes over because Aline cannot be here, and who is also sick, and Daniel is so kind to take over, right? But Daniel, again, he's kind of a doctoral student here from Bremen, a former one, and yeah, he won the best dissertation award of European robotics a couple of years ago, and he's heading a kind of a research team at the DLR at Oberpfaffenhofen, and yeah, so he is kind of doing very excellent work in the terms in the area of robot planning, and in particular now execution failures. And I think Daniel will also tell us a little bit about something that should interest all of us at the moment, and this is kind of the network of excellence centers in robotics, which is currently forming, and which we hope that partners are joining and make it bigger. And yeah, so that network is called EURobin, and Daniel, thanks a lot for taking over and giving that presentation.
Thank you very much. So exactly. So I'm taking over for Aline. I was informed just in time yesterday, and also my presentation got ready just in time because of the shift now. But I think we'll be fine. Maybe we'll improvise a bit. But in general, so the presentation that Aline wanted to give, and he's really sorry that he could not come because he is really much appreciating the collaboration with Bremen, is about intelligent assistant robots designed and programmed for direct interaction with humans. And actually, this is already leading us to a big question. The big question that was given or asked to us by the European Commission, and it was about how can we overcome the great challenges that hamper the deployment of robotics in the domains of our daily life. And this was exactly the question that was raised with respect to the research call on that then resulted in a project, and the project is called EURobin, as already introduced. It's quite a big project already. It's 31 partners, as you can see here on the slide already. And we hope that it will be, there will be even more, because there is a possibility for others to join and make the network even more effective. Because you can see on the right hand side that we want to have a network that is really really strong also in exchange between people, in exchange between scientists, but also with respect to industry. There shall be an outcome also beyond the project. And therefore, we have a central element, which is called the Eurocore, which we will also learn much more about tomorrow. And I think the most interesting message for you right now from the beginning is that this is something that does not only concern the people that are here, but actually all of you, and we will be really happy if you could join. So what is it about? So the idea of Eurobin was to use information from different robots on different other robots. And we were wondering how you could try to achieve that. How could you foster that? And then I think it was in a conversation between Aline and Tamim Asfour when they had the idea of cooperative competition. That is, robots like these that you can see over here will try to solve one task, but they will not try to solve it alone. Well, in some sense, yes, but they will try to share knowledge to make another robot in the next round better in the same task. And so it's consisting of 3 tasks. This is actually only one that I'm sketching here. It's about the personal robotics challenge. And this is certainly one challenge that we are trying to face here. And in the first year, for example, think about that. There will be a parcel delivery, and the robot needs to fetch the parcel, bring it to a table, unpack it, and get all the goods out. And in the second year, the goods need to go somewhere. They need to go in refrigerators, they need to go in a dishwasher, they need to go in cupboards, drawers. And the first year, this object will all be rigid, and then also in the second year. And then in the third year, there will be semi-rigid, so think of noodles. And then eventually, we even hope to be able to manipulate soft objects in very complex situations like loading and unloading a washing machine, and maybe even hanging these clothes on a hanger. So it's really, really challenging, but it has to be challenging because otherwise, I don't want to say we could do it alone, but it needs so many different strategies that you need all the specialists from all over Europe. So this is what it may look like. So think about 3 tasks that 3 robots would execute simultaneously. The first task is to receive the parcel from the entrance. The second task is to open the parcel with a cutter, with a knife. The third task is to detect the objects in the box and unload them. And for all of that, you need some preparation phase. So you need to create a map to reach the door. You need to maybe learn a skill for cutting. You may need to train a neural network such that the robot can actually detect all the objects and unload them. But once a robot has done that, all this information could be shared between the other robots, and they could be much faster, as you can see it in phase 3 and phase 2. But it's really important to understand this is not about exchanging software. We learned a lot about exchanging software with Ross, but this is more on a higher level of abstraction. It's about how can we create knowledge that is universally applicable by different robots, such that they can perform much better in these tasks. So, and as this is quite a challenge, we have founded this network, as you can see here, and there is several activities already introduced, and in the core there is the EuroCore, where we will store the data, but to access that data, to utilize it, we will have 4 scientific work packages, experts of the field of learning, knowledge, obviously, human-centered robotics and interaction, also new materials and stuff like that. And they will leverage the information from the EuroCore and provide it to the challengers that you can see on the outer circle, which are the challenges of personal robotics, outdoor robots, and robotic manufacturing. And as I said, a lasting impact is really, really important. So this is why we want to have also exchange with industry right from the beginning. And there's already quite some industry partners there, and we hope that there will be also more here. So I'd also like to give you from here on now a DLR perspective on how we how we approach these problems at our labs and what our inputs will be. And you can see here already this is quite different from what you are used as a robot, but this is actually a retrofitted robot. It's a Sherp amphibic car that is meant to deliver goods. And this is all about the first challenge. The first challenge is about delivering goods in areas that are difficult to access. You may need even drones for that or other devices, maybe even something like that. So this is actually a photo of our rover that was executing some unloading task here on Mount Etna. Drones are obviously part of it. But when we talk also about outdoor environments, we often talk about space in general. And the same methods that we will apply to EU Robin, we actually developed them initially for space robotics, and this is what we will focus on the first part of the slide. So imagine this situation. You can see on this slide that there's astronauts, that there's habitats, that there's cars, there's quite some infrastructure, and I want to ask you a question. If this environment is hostile for humans, who will set it up? Robots. Exactly. So it needs to be robots that set that up, because it's quite time consuming, and if you think about a 30-day mission to Mars, actually all of that also already has to be in place. So we would send our assistant robots. We would send Justin, for example, but we would not send them alone, because we would send them together with astronauts in the orbit of Mars. This is similar to how they did the first experiments and the first missions to Moon. First, the astronauts fly to Moon, make some observations, make some research in the orbit, and then they fly back. And it also is varying a lot. So you want to have something more intuitive, and this is where like an interface, as you can see it here, comes into place, a tablet-based interface with high-level skills to control the robot. And this is how that looked like. So this is a video footage that is assembled of the first Meteoron experiments that we had in 2017, and then the further ones in 2018. So this is Justin. This is Paolo Nespoli on the International Space Station, Scott Tingle, NASA astronaut, and we also had the German astronaut, Alexander Gerst. And they were, as you can see, they set up this infrastructure in their environment, in their space station. It's only a tablet, as you see, and the astronauts see what the robot sees. They see through the eyes of the robot. They may have an overview map, as you can see it here, and then they control the robot to perform quite some complex tasks. Here, for example, taking an antenna, moving it to a smart payload unit, as we call it, and then we even added a failure. We added a damage to the system, and the astronaut would never know before what would happen. So this was a completely new task for them. And in this case, Alexander Gerst, he actually only trained for 20 minutes, and we made it as challenging as possible, but nevertheless, he was able to resolve the problem. So he was able to identify that he needed to open the door, look into the inner of this smart payload unit, identify the broken piece here, and then remove it. And all of that is done by means of planning. So the robot is doing all the planning on its own. So the astronaut only gives actions like, please grab that box, close the drawer, close the door, take this and that, bring it over here, and so on and so forth. So that's quite challenging. And the action representation that you need for that also need to be quite powerful. They need to also be intuitive, and it looks like that. So for every action the robot can execute, there's the so-called action template. So we have seen motion templates in the previous task, and this is about action templates. Action templates describe an action based on semantic information in a header. We are using PDDL for that, and this is also how we can extract the actions for the operator. And then the second part is a geometric representation, which is a parameterizable, again, a parameterizable representation of the action, where the robot then is able to integrate its motion planning capabilities, different controller capabilities, and so forth, also navigation, to solve the problem. Now, in Surface Avatar, which we just recently executed, actually the last experiment we had 2 weeks ago with Jessica Watkins, an American astronaut, we try to now integrate also different modalities, because way back we had experiments with astronauts where they only had force feedback, and they always asked for autonomy. And when we had the task about autonomy, people were like, can I have more control? And so now we give them both of it, and it turns out that it's not so easy if you give them choices. They usually take the wrong one. And so this is actually an interesting picture, because you can see here this is not the fault of the astronaut, but this is the fault of the robot. So we actually had also again introduced an error here. You can see that, is there a pointer? No. You can see here that the robot failed to insert the plug, and we made it on purpose because we wanted to see if the human can now take this device and fix that problem. And as you know, as Michael introduced it, so actually within EASE and also earlier already, my work was about identifying failure situations and try to fix them. And at some point, maybe they are no longer fixable, and then we just give them back to the user, to the astronaut in that case, And this is what you can see here. So now the robot identified this problem. We are using digital twins for that. So there is a reasoning framework where the robot is able to identify erroneous situations such as this using semantic information derived from digital twin knowledge. All right. The second domain that we are looking into is the personal robotics domain, and this actually derives from what we have seen before. So we had the task of unloading the dishwasher seen before. This is David, one of our robots. We have also seen how we can teleoperate robots. This is one of our robots, it's Toro, it's a bipedal robot. But then we again have Justin here, and we have Eden, a wheelchair-based robot. And you should know that if you want to do things like servicing a person, it kind of boils down to the same request as servicing a planetary infrastructure, because you need to have interfaces that are really, really easy to use. So the two interfaces that we have are these. So there's one about the direct control using, as we see here, a force feedback device for an operator, but then also more easy to use interfaces for relatives. So everybody could control a robot. If, let's say, your mother calls you and she needs some assistance in the kitchen, then you would just open up your phone and say, alrighty, I can make you some, I don't know, healthy salad. And the robot should do that. So it should be as that simple. And whenever you are no longer able to solve that problem, then you call for assistance and an expert gets into the control and controls the system. That looks as follows. So you should notice that in this case, the same infrastructure is used as in the Metron experiment. So there is a colleague of ours controlling the robot with a touch-based interface for everything that is related to, let's say, standard tasks, opening drawer, grabbing objects, and maybe even driving somewhere. But as soon as it gets to the point where you want to get into contact with a human, it may be tricky also for, or maybe even uncomfortable for a person that is on the other side to get actually treated by the robot. So therefore, here, the expert is using another force feedback device. It has much more workspace, so it's easier to use than what we have seen on the space station. And it gives the user the full immersion here. So the user sees what the robot sees, and they can feel what the robot feels, and they also are limited here to some thresholds, for example. They will never be able to hurt a human because the forces that are exerted are just limited to what is reasonable here in that case. So as you see, there's quite some differences in control modalities, and this is important if you want to interact with systems. So on the very bottom, we see autonomous manipulation using voice commands. So this is what we have seen in the presentation of Kay. So this is really, really something that we would like to achieve. But in the meantime, there's different ways of how we could interact with a robot. And I tell you that there's also always the need for direct control, because we will see it later, some users demand that. So, for example, these users. This person is a person in a wheelchair, and you can see that she is really, really skinny, and this is because she has spinal muscle atrophy. What does that mean? So she is essentially unable to move at all. And as a result, her muscles degenerate. And what she's doing here is, though, trying to control the robot using leftover EMG signals from the surface of her skin that still make their way from the, let's say, broken nerve system to the muscles, but they are no longer able to actuate the muscle. But still, the noisy signals can be used to identify if the user wants to go up, down, forward, backward, but only these ones, really, really simple motions. And here you see that it's like a relief. Like you can see her really smiling. It's something that she wants to do. And even if it takes like 3 hours, she wants to do that. But we at least want to reduce it to, let's say, an hour or maybe 10 minutes or maybe 5 minutes. That would be already really nice, but still keep these persons in charge. So how do we do that without sacrificing the autonomy of the person in that case, right? And this is why we have identified a second interface, which we call shared control templates. This is actually inspired by some work of Georg Bartels here of University of Bremen. It's a constraint-based interface, or a constraint-based action representation. And it works as follows. So given this interface, as seen on the very top left, which are the EMG sensors on the skin, they only come, let's say, in 3 signal dimensions. And these dimensions need to be mapped to a certain task. Pouring, for example. So with 3 translational inputs, you could never rotate, right? But if we know what the system is about to do, if we can anticipate what the user wants to do, we can map the inputs to something that is more reasonable for that certain task. For example, here rotation in the first phase, and once you are over the glass and you want to pour further, you can be fancy and then go up and down, or go just back, and that's about it. The way of how to execute the motion on the robot is defined by then these so-called active constraints. So for all the phases that, for example, here in pouring, a robot needs to execute, the motions are restricted to what is just for this single task reasonable. And as I told you earlier, all the users always want what they never have had before. So we gave them the direct control, and at some point they were like, oh, that's boring. Can I have it autonomous again? And so we thought, okay, how can we now integrate autonomy again using this interface? And there is now a new or combined action representation, which is actually developed within EASE. It's the constraint action template. So it's combining the best of both worlds. Action templates, shared control templates, we've merged them to cats, so to say. And these cats first start as a template that looks almost like an action template, but is way more annotated. And with this annotation, we can identify phases. And from that phases, we can auto-generate shared control templates, as you can see it on the right here. And they can be executed autonomously by the robot, just providing some input to the system, just as a user would do. And then you can even press a button and the robot does everything autonomously, even to a multi-step action. Right. And this is, again, a video how that looks like. So this is quite a difficult task. So you can see the person here in the wheelchair. This is Annette. She's perfectly healthy. So she's not using a EMG-based interface, but she's using a space mouse. But nevertheless, she's not directly controlling the arm. But what she's doing, actually, she's controlling that input vector. And you can see here the input vector now, she's only pressing forward, but the robot is already approaching the door, and then it's already starting to rotate because the system knows there's a camera on the back, that there's a door in front, and that the task must be opening a door, because if you're in front of a door, there's not so much you can do with it. So the system, just by pressing forward, just goes and opens and rotates the arm now, and then the wheelchair starts without the user having to switch to the wheelchair. So everything goes on and on and on until the door is then done. And then if you are turning around and you will be in front of an open door, then what should you do? Well, you can close it then, and essentially this is how the system works. So there's an inference ongoing all the time, and then the system is anticipating what the user is trying to do. And if there's some ambiguities, then the system will just give the user some options to select from. And as you can see, there's a head button, so the users can still press the head button and switch to the options and do other things. All right, so yeah, considering time, I think I'll go further here. So the third domain that we're looking in EU Robin is about robotic manufacturing, and also obviously here, I mean, you know, the lightweight robot was initially built for industrial manufacturing. We have quite some work done. This is our latest lightweight robot, Sarah. It's quite capable. It's a prototype. We at the moment have 3 of them, but as you can see what we're doing here, so we are inserting here rotors, or actually drive engines of a chainsaw using this system. It's quite capable in terms of precision. We also have human collaboration in industry. That's something that is still required at the times being, also considering that if you have a robot to a worker, you will be able to actually, yeah, let's say, amplify the workforce of the human in that case. And then what I'm actually will tell you about is something different. It's about mobile manipulators. So mobile manipulators have been quite around for some time, and we use them, or we try to use them, or bring them to the people in industrial settings. But it turned out that somehow this is not what industry wants, right? It's either something fixed, or it's something semi-flexible, but mobile manipulators are still rarely seen in factory halls. But with the upcoming of the pandemic, actually, there was all of a sudden a use case. And I talked to different peoples, And I talked to, here, Andreas Kurt. He's the head of the high biosafety level, the BSL-4 laboratory of the Robert Koch Institute. And we were talking about what you need to do in such a lab and how you can work in there. And then he said, you know, actually, a high biosafety laboratory is like the space station. And then I thought about it, and he's right, look at that. So this Tim Peake aboard the ISS. And then there's a person at the BSL-4 laboratory at RKI, and this looks really, really similar, and it has the same problems. So humans that go in there need to wear this sequence here. A human does nothing else than filling these machines all day with the samples taken from some person. So this is the entire task that you need to do in a PCR test. Obviously, there's fully automated PCR machinery at the moment. But if you think about a new pandemic, a new virus, then you don't know what to do. And you make every day another test. You try to figure out what is the problem. You try to figure out what is the virus about, and then you need to be highly flexible. And this is where the robots come in. So we scanned the systems, and it doesn't look yet like what Michael usually shows. So I'm aware of that. So this is where we need to work on. But you see that what the task is about. It's kind of repetitive. It's actually almost easy. You need to take care of the orientation. Well, there's a constraint, but in that sense, then you just do that, filling these machines, and then you close them. So this is what we're currently working on. We have just started a project. So this is yet only in simulation, and we hope that we can go next year to the DKFZ in Heidelberg and actually have our robots performing these tasks in that laboratory for quite some time. All right. This is what it looks like. We had some tests with our robot, but more interesting is actually going back to EU Robin. I told you that there's possibilities for interaction, and this is here on the left side, the cascaded funding. So starting from March and then going, I think, into a half-yearly turnus, we will be able to give out calls for participation. And there will be calls for people that people that would like to use their own robot and bring them into the challenges and try to solve some problems. And there will be calls for scientists that just want to provide the existing challenger teams with some modules. Let's say a model for solving object detection, a model for detecting humans, a model for folding clothes. And if you think that your solution is a good one for that problem, then you are very welcome to apply. I think that we will be able to distribute the information through the usual channels and maybe also Michael and all the networks that we have. And it's about this one. It's about from a network of roboticists to a network of robots that will be deployed eventually into society as we were asked by the European Commission. Thank you very much.
I guess now we have lunch break, right? Yeah. So as I said, so the labs are open. You are welcome to just look around. Okay. And yes, have fun and yeah, use the opportunity to talk to each other, to connect. I think we haven't seen each other for quite a while, and yeah, so have fun. Yeah.
腰を下ろすか横になりましょう。瞑想を始めましょう。目を閉じて大きく息を吸ってそして吐きます。何も考えず部屋いっぱいに広がる優しい落ち着いた音楽が心配事もない静けさ清らかな静寂へ導きます。体を完全にリラックスした状態にすることができるのです。呼吸に集中しましょう。さあ、酸素があなたの鼻をゆっくりと通り息を吐くときに考えましょう。肉体的または精神的なあなたの痛みについて、あなたは一人ぼっちではありません。心配や疑念などが入り込む余地のない
Okay, so let's start again. So it's my pleasure to welcome you here, and it's kind of the first time I give a talk about a lab, right? And I think it'll be a very interesting talk for me. Also, I think the newest videos in the talk are from 3 o'clock, and I'm also curious to see them. Yeah, so what I want to do is, so as you all know, we are introducing this new lab, and I want to basically present you and give you some ideas about why we want to have that lab and why we think it's important, right? And so I think as a research community, we are very privileged, right? So we are actually doing research on one of the grand challenges of science, and this is understanding how the brain is actually able to accomplish intelligent agency and how we can build computer models from that. And even if we look at sub-problems of that task, they are of enormous complexity. Right, and the sub-problem we are kind of most interested in is the computational problem given a vague task instruction. So something like set the table, bring me something to drink, kind of clean up. So the task of a robot is to take that vague task description and to compute a body motion that achieves the desired effects and avoids unwanted side effects, right? And that's kind of tremendously complicated because we have to imagine in our head the actions that we are going to execute. We have to think about hypotheses, and as Giulio has said, I think it's just a tremendous science problem. So, but it's not only that, right? So if we would solve the problem, we would have something like AlphaGo, a system that kind of computes the next move in a perfect way, but that wouldn't understand what it's doing, right? And if we look at AlphaGo, it can compute the best next move, but it could not play to let somebody win or it could not play to teach somebody AlphaGo. It doesn't know how the board looks. It doesn't know how the systems work. So even if people tell you that in the terms of general intelligence we are doing well, we are no match at all for what the human brain is actually doing, right? So the problem is kind of doing that, but in addition, to understand what one is doing, to take advice. Advice means getting some information in natural language and being able to reprogram oneself in order to reflect that advice. And I think the most complicated and the most challenging aspect is accomplishing tasks together with humans, right? And by together with humans, we mean that the robot is actually having the same conceptual framework to talk about the world and to exchange ideas as humans have, right? So how big that challenge is, you can just see by looking at a tiny part, a tiny puzzle piece of what we are doing in our daily life, right? It's kind of a Bavarian breakfast during Oktoberfest, right? And if you only look at the pouring task, so you have to pour Weissbier into a glass, right? And you have to pour the water out of a pot with Weisswürste. You have to pour honey on the roll, and you have to pour pancake mix on a pancake. And so all these pouring actions, they are with different substances. They are pouring out of different sauce containers. They are pouring to different distances, to destinations, and they pour for different purposes, right? And each of these individual tasks requires a different behavior patterns, right? And what we have to do is we have to find the right behavior patterns for each of these combinations. And that is not including things like pouring water in order to extinguish fire, which is kind of a completely different thing, or neutralize acid or something like that, right? So going for that challenge, right, for that long-term challenge is a huge research enterprise, and it requires many research missions. If we want to get there, right, so at least in my view, we need robots that can watch instruction videos in the web. They can watch WikiHow, read the instructions and turn them into actions, right? They have to be able to do the housework, so setting the table, cleaning, loading the dishwasher for a robot lifetime. They have to kind of not only learn how to perform one specific task, but they have to learn the tasks themselves, right? And in order to do that, they have to interact with a teacher in a very competent way, and also we would like to have robots that learn like humans, right? So so the kind of the thing is that if we are looking at the research community, there are comparatively few research groups actually looking at these big challenges. And the reason is most likely that in order to actually tackle these research missions, you already need a robot with basic cognitive capabilities, right? And you need that robot as an off-the-shelf robot that already works, and then you can push it, right? But these robots currently don't exist, right? And that's something that we know for a long time. So I think the most famous place where that was actually pointed out was by two Stanford students, Eric Berger and Keenan Wirobek, right? They had kind of the vision that one could start a Linux community for robotics if we only build a basic autonomous mobile manipulation platform with a basic software, and they equip 10 leading research labs in the world with a robot, and get the people, the community going. And by doing that, so we are able to kind of start on the same basis, and we don't have to reinvent the wheel and always kind of build the robots and wasting time and efforts, right? And we know that this vision of these two Stanford students, this vision became Willow Garage, kind of the most impactful robotics company in my view. And they built the ROS middleware operating system for robots. And so for me, it's the most successful robotics failure, right? It's a failure because we still don't have these fully functional autonomous robots, but it's kind of the most successful one because it has built a huge community of robotics researchers. Today, I think half of the commercial robots are actually using ROS components, and I think they just opened the way to have many billion-dollar market and made that possible. So that money was very well invested. So, but I think, so as a community, we still have to revive that idea that all of us need kind of fully functional autonomous robots that do manipulation tasks, right? And in my view, I think we have to give such a robot to every student, every researcher, every research team, every project, and also to the general public, right? And the question, I think, Willow Garage and ROS were a very exciting and cool example of how that can go. Another one is YAP and ICAP, right? But let me go and see you what I think is necessary in order to make that vision work, right? So if we want to have the cognitive robot that Giulio was talking about, right? So we need three things. We need the robot, we need the environment that the robot is interacting in, and we need the human the robot is working with. So these are the three things. And if we are an open research, open source community, we have to make the program that the robot is using open to every researchers, right? So that other researchers can build on top of it. Then we have to take these three things together, and we have to build a real lab. So a physical lab that people can come to and do research with the physical platforms on site. We need a very powerful model of that environment because we are scientists and we want to basically make experiments, and the experiments need to be evaluated with respect to models. And if you see today's state of the art, I think it's the models, they do not only have to be very detailed, very accurate, but they have to be machine understandable. They have to be machine interpretable. So everything has to be AI ready, right? So that we can actually have our programs and directly connect them to the model. And we need another thing, we need a digital twin. So we need a software of the real lab, a software duplicate that we can basically do research on without having to move the robot in most of the cases. Kind of these three components, if we are looking at those components from a science perspective, they are producers of data, right? So we collect data from the real lab, we are collecting data from the model, or we use the model data to interpret these data, and we collect data from the simulators. And these data, they make the experience knowledge of the robot, and we have to turn them into knowledge that the robot can use. And we also have to connect the experience knowledge, and this is kind of what distinguishes us from approaches from applying pure deep learning. We have to connect them with the knowledge in the World Wide Web, right? So we would like to kind of have the Wikipedia machine understandable and make our robot use it. And we need something like large language models that are learned by deep learning, but also connect them to the perception action loops of our robots. And that's kind of what we need here. So if we have that whole thing as a software packet and we can use it, then we can actually use those as tools, for one thing, for research projects, large cooperative research projects, where some of the partners do different parts of the robot control program and they combine it. We can use them for science, so where we basically have something like knowledge representation and reasoning as a topic area, but we want to have different methods, and these different methods should be comparable by being applied to the same environment. We want to use that software infrastructure to have a textbook where you can go into the lab and do research-oriented teaching and training, and just use that as part of your textbook. You want to use these infrastructure in order to develop digital innovation platforms to connect kind of producers of software, for instance, hardware components with consumers. So for instance, you want to connect companies that produce robots for retail stores with store managers of retail stores that provide a model. Small part is a physical lab, but the idea is a much bigger one. And I just want to show you some of the aspects, and I would like to invite you to go to the different rooms and look at the different components of our lab. So the first thing is the lab itself, the hardware, right? So what we have is a very nice apartment, but we also have a second kitchen environment, and we have a retail store, and this is kind of a variety of research environments for robotics, which is, I think, quite reasonable. We also have different autonomous mobile manipulation platforms that you can run in the different environments, and we have other setups, a lab robot, and kind of even a simulation of an underwater robot. But what is really kind of the question is, why should others actually use or work in our lab? And I think the key argument is the programs that are actually accessible by going in the robot. And here you see, and this is Gayan's dissertation thesis, the robot doing pick and place tasks. And the amazing thing is it's an identical program plan doing all these different things. It's a pick and place plan that essentially says, go where you think that the item is that you want to do, and pick it up. And it's basically running on different robots, different environments, different tasks. And it's in all cases, it's the same program, right? And the amazing thing is that this program is not only kind of specifying the behavior of the robot, but when running the robot can also answer questions about what it's doing and why. Right? And I think we all know that generality, transferability in AI, I think is one of the big tasks we have to focus on in the next years. Then it comes to the model, right? So we want to have a model of the research lab. And so the model is kind of a virtual reality model that is photorealistic and very detailed. And so the interesting part about that model is that it's not only a geometric and physical model, but it's at the same time a knowledge base. So every item that you see here, essentially, you can ask questions about, or you can ask kind of, what are you doing? What can you be used for? You see the level of detail we have in the model, and also that we want to have manipulation activities that join that. So the thing that makes that all possible is that we are representing the whole environment as a scene graph in a virtual reality environment, right? And we use that scene graph as an implementation basis for a symbolic knowledge base. So when we ask symbolic questions about the environment, the predicates of the symbolic knowledge base, they compute the answers on demand out of the scene graph, right? So, but that means conceptually, the whole scene graph is the knowledge base of the robot, and it can be, because of game technology, be maintained in real time. So that's kind of very interesting. So here you see how the environment is constructed out of a prologue knowledge base. It's essentially taking the objects, spawning them, but now we can ask all kinds of questions, and it can be answered using these models. So the query language is essentially a very sophisticated database query language, right, with semantics. And you can use the language to formulate any language, any query that your predicates give to you. And now all the experiences that we collect in the environment, they are stored in a web-based knowledge service that is interactive, where you can ask queries and then the system retrieves the respective episodic memories. And if you ask about a certain action, or here's something, an object that affords grasping, then it would return the answer, and it also works for retail stores. So, but again, the big idea is, if we have digital twins and we scale them, these digital twins do not only have to be a virtual reality environment, but they can be a symbolic knowledge base. So now, because we have the digital twins in the scene graph representations, we can have powerful simulation environments. We can run our table setting demonstration in the simulation environment. See here that the behavior of the robot is very similar to the behavior in the real setting. And we can develop essentially the programs and do our research in a low-cost way, because we don't have setup, we don't have physical risks for the people participating, but then we still get all the information we need in order to do our research. And here you see some of the sophistication where we want to push the physics simulation kind of to be more and more sophisticated in order to for one thing, so that robots can learn from humans, and for the other thing, to actually get robots doing physical manipulation actions more competently. Right? This is also interesting because this is actually a model, a digital twin that is generated by a robot, and that is done by our startup Ubica. That basically sends robots into retail stores, build these semantic digital twins of them, and here we bring the models back and use them as research vehicles for our field. And here another example that's actually also a COVID testing lab scenario where the digital twin is used to verify that the manipulation actions that are executed are successful, so which is kind of very important in the medical domain, as Daniel has pointed out. The hardest thing about having that kind of environment for doing research, in my view, is having the human. I think the human is, you can't imagine a robot doing serious manipulation tasks in the presence of the human, being safe and get that running. So I think in order to get the human in these manipulation settings, we have to include virtual reality solutions in order to do that. So here are some of the components that we are using. So the first one is actually taking a normal gaming setup. So we put the humans into our kitchen environments, and we run them. So this is more interest. So here, the game is that we use cameras, 3D cameras, and we want to build models of humans that are avatars, and we want to clone these avatars in our digital twins, right? And now we read the gestures and the motions of the humans, and if we are executing them in the digital twin, they have physical effects, right? So we can actually test whether what we are seeing is right. And we have another setup where we are starting to try kind of watching instruction videos from YouTube or WikiHow, where we get these data by letting the robots watch the videos. So all that, the purpose is to actually make the knowledge of the robot more comprehensive and to be able to scale towards all these different variations of manipulation tasks that robots have to accomplish in open worlds, right? So in order to automate that, we are recording all the data and we collect them in episodic memories. So episodic memories are like the human memory system. We remember the scenes we have executed, right? And we are processing these episodic memories again as knowledge bases. So they are automatically segmented and into models that are used in cognitive psychology. And again, we can use these models to answer all kinds of questions about manipulation actions, right? So if you compare that to data-intensive machine learning, the big win here is that we can kind of run hundreds of different learning tasks at the same time about different things, and we just collect the data that is there from the experiment, right? And so we expect that kind of, I think we had that in a previous talk, robots have to learn from observation, right? And observation is something they don't have to do, but in observations we can learn many different things. So this is how you get these access to these episodic memories in our open knowledge service. It's a web-based knowledge service. You're asking about actions, and you're getting now the knowledge being represented as a symbolic knowledge base, and you can have just questions like give me an action with some goal, and the action has a deeper model. And because everything is a knowledge base, you can click on every component, you can get this component, you can ask for examples or in which events that happen. So it gives you basically access to a knowledge space. So we are also using that in the project Knowledge for Retail as a digital innovation platform. So we connect people in the retail business, and so applications like the one that Benjamin showed, and producers from hardware like Ubica, and we have a common platform where we have an ecosystem where all the players in the market can actually work together by having the semantic digital twins as a basis for implementing the cooperation. I think one of the things we are particularly proud of is that we have also acquired a project where we plan to take the same technology and bring it into teaching, right? So what we want to have is we want to have an open textbook and an open teaching environment for cognitive robotics. So that's the project Intel for Coro on cognitive architectures. And if you're going back from the videos, you're going to the exercises. And if you're clicking on the exercises, you essentially load our lab and the robot control systems in that. And you have editors in your textbook where you can develop your programs, where you can change your programs and try them out in the environment, right? So I think that is our way that we want to promote research-oriented training, and that we want to get students very early in university kind of familiar with cognitive robotics, and try to acquire them to make a career in that respect. Okay, so let me just finish up. So the idea of that research lab is that it's kind of a huge software component, right? It's a huge digital twin, and it has actually a physical implementation, which is here at this university. But this software environment, right, so that enables kind of research projects to where basically partners develop different components to develop a demonstrator of their research results together. For research fields, it allows researchers with different methods to compare and benchmark their different methods in the same environment and to share actually the task they are thinking about. We have seen that the lab is a basis for an interactive textbook and immersive learning. Also that the lab essentially is a connector between producers and consumers in a digital ecosystem. We can use it as an arena and an intelligent logging mechanism for competitions where we have different teams competing with each other and refereeing on that. And of course, what is important as responsible researchers to put citizen science and get the public informed properly about our research. I guess, and of course, the big thing is also that that's a tool for forming communities, right? That kind of the people in robotics can work together in an easier way. And so my dream is actually, when we look at a project like Eurocore, that 3 different labs are actually presenting their labs in that way. And this way we get kind of a much bigger community, we get more synergies, and we can share our research progress more effectively. Okay, so let me end. So what I wanted to get across is that cognitive robotics is one of the grand science challenges that we have at the moment, and that we can be happy that we can work on that challenge. It's also a huge potential innovation motor for kind of commercial applications. And it's a technology that we urgently need to meet some of the societal challenges, right? So making cognitive robots real is, for me, requires a community that works together in order to do that, right? So companies, big companies have huge teams, but universities don't have that. So we have to be a kind of a team by building the partners from different universities. And it requires a powerful research infrastructure. And we hope that our new lab is a small step in that direction. So thanks. And I hope that you all... Just one more addition, thanks a lot. I hope that you kind of go and visit kind of the researchers in the different labs, and you kind of have a closer look, and that, I mean, the doctoral student enjoy feedback from you, and yeah. So thanks a lot for being here. Yeah. Cool. So now I'm going back to the moderator role. So I think it's not that I have chosen that position, but I think the last days they were so chaotic that I didn't point somebody to being a moderator, and I ended up to having do it myself. But nevertheless, it's my big pleasure now to introduce Tanya. Tanya is kind of dear colleague here from the department, and she is a co-coordinator of our research focus area, Minds, Media, Machines. She has gotten the ITSCAI to Bremen in 2026, I guess, yes. And yes, so, kind of a very successful researcher in interpreting body signals from humans and coming out of natural language. And yeah, it's a pleasure to introduce you, and I look forward to your talk.
So thank you very much, Michael, and thank you very much for inviting me to give a talk. Actually, he was challenging me. He told me, Tanya, give a talk and tell us what your biosignals of human beings can be used for in the case of robotics and in his world. And I reached out to several people you see here. I reached out to Felix Putze, he's a senior member of the CSL, my lab, and I reached out to Britta Wrede, who's now a professor here at the University of Bremen, and she also brought in Katharina Rolfing from University of Paderborn. So what you see here and will hear in this talk is a tight human-human collaboration discussing about human-robot collaboration. And this is what we came up with. And originally the talk was Perspectives in Cognitive Systems, but we gave it the subtitle of Co-construction of a Scalable Joint World Model. And I will walk you through what I mean with this. But one thing which is very important is on the center of the stage for this talk is not the robot, it's the human. It's the human being, and I started out thinking, okay, for me, what are the promises of humanoid robots to me or maybe to my older me? And I think that humanoid robots should accompany and support me so that I could lead, if possible, an independent, but at least a self-determined life for as long as possible, at home, at play, or at work. And in order to do that, and we have heard this morning from Giuliani, is that robots and humans will share spaces, tools, objects, and tasks. They will interact with each other to achieve a goal. And this interaction could have several ranges. So it could go from coexistence, which, for example, could be the mowing bot in the garden who's mowing the grass. So we negotiate once that he does the grass and I do the work at home. And then this is basically coexistence. But it could also range all the way to collaboration, where a human and robot really work together to achieve a joint goal or a goal. It could also mean, if I picture myself with a robot at home, I believe that robots and humans should learn from each other, probably even over the lifetime. That could mean that the robot learns about or from humans, and the humans learn about robots or from robots. Nevertheless, how close this collaboration will be and how the learning will be, but I believe, or we believe, that this needs for a consistent, incremental cognitive model of joint tasks or a joint world. And so if we put this idea out, so in an ideal world, and we put this into the scenario of ease in the kitchen, so in the ideal world, I figure myself being in the kitchen, maybe start cooking, and I just need help, but I don't want to explicitly tell the robot what to do. So the vision would be that I start cooking, for example, I could say, let's cook a soup, can you give me a hand? And I know maybe from earlier engagements with the robot that the robot certainly is not good yet at doing the chopping, but I want him or it to be supportive, and I expect the robot to figure out from my social cues and from my behavior what really would be the best to support me. So what's required is a human model of the robot, because I need to have a certain understanding what the robot can do and what it can't do. But also we need a robot's model of the human so that the robot can start inferring what might be a useful thing to do to help me. So the first step would then be that the robot is able and capable of observing my behavior. So it's observing and also interpreting behavior. This could basically be the full range of biosignals. With biosignals, I mean the full range of signals that the human body is emitting while behaving. This could be speech-related signals, this could be brain activity, eye gaze, and whatnot. And the robot should be able to observe all these biosignals and interpret them to understand what I'm doing, why I'm doing this, and in which situation activity I am right now. So in this particular example, the robot would, for example, take speech recognition, automatic speech recognition, to figure out what I had said, and then use natural language processing to derive that I talked about cooking soup. So the first slot in the model of the robot would basically be filled by doing automatic speech recognition. Then the robot would probably check out my eye gaze and would figure out maybe that I'm looking to the cabinet, maybe looking at the pot which is on top of the cabinet. The robot knows probably from earlier engagements with me that I have an impairment, I cannot reach very high. It would also figure out from my brain activity that I have a high cognitive load. and it would figure out from natural language processing and a discourse model that I requested manual help by asking, can you give me a hand? And all of these analysis coming from biosignals, but also coming from motion capturing and videos, the robot should be able to infer that it would be a helpful strategy if the robot reaches out to the cabinet and gets the pot for doing the soup. So what we already have available is, like Michael already showed in his talk in a very impressive manner, that we have available this whole planning and execution of motion. So this is all there. The robot can go to the cabinet, it can pick and place the pot, it can reach or put it somewhere. So what it needs is it needs to be able to infer from my behavior what I need, and it needs to reason also from the behavior what I need, and to make a decision what could be the best strategy to support my actions. And in order to do so, we believe that what we need is a cognitive model that includes the robot's view of the human, but also includes the human model itself. And this cognitive model that we would need, we can plug into the CRAM world to do a simulation, to do basically the Probehandeln, if you will. And we need also some strategies for doing causal inference so that the robot could figure out what a good strategy could be. And this construction of a model, in our view, can only happen in a joint world, so it has to be done in tight collaboration between the robot and the human, and it needs to integrate the human behavior, which means a model of the human. And the approach we believe is suitable for doing such kind of a model is co-construction. So what we would like to achieve is we would like to co-construct a scalable joint world model. And the scalability of this model, we believe, could be proved by co-constructing new tasks. So this is sort of the idea. And in case you wonder what we mean by co-construction, we have here a working definition of co-construction. So with co-construction, we refer to the process of learning, teaching, and collaborating, where both partners, in our case the human and the robot, work together toward a joint goal. And during the process, all the relevant aspects of the problem, such that the precise goal, the means, or the necessary concepts, they may only become clear by both partners contributing their respective knowledge, their values, and their assumptions. And so the co-construction, we believe, pertains to multiple levels, such as action, interaction elements, or also representations. So the co-construction, in our view, has two directions. So there is the direction of, we call it human to robot. This is the upper case, where it's the robot's task to observe and learn from the human being. And it's the human being part to teach the robot, for example, by using scaffolding. So this is the upper loop. The lower loop is where the roles are reversed. That means the robot is the one that provides the teaching, and the human is the one that does the observing and the learning. So co-construction can go in both of these directions. And in case you wonder what we want to co-construct, here also certain levels can be achieved. So for one, we believe that we need a joint, consistent representations of the agents, that means of the robot and of the human. And we also need a representation of the environment, which is the world. And these representations include those things which are observable and those which are not observable, like, for example, internal properties of a human being, mental tasks, for example. It also requires a meta model, so it would also involve co-constructing a meta model, like the part of the modeled properties could be models themselves. And another route of co-construction is that we want to co-construct skills. That means an agent learns a generalized skill through a mix of observation, teaching, or joint execution. Now, how would this look like in our scenario? So in the first iteration, we have the human has probably a mental model of what the robot can and what it cannot do. So in this case, for example, the human could think about the robot is very strong, but it's not a good or a correction during the joint execution. That is, the person realizes that the robot is doing something and then provides, for example, with the gaze, provides information where the pot is supposed to go. So the robot basically has now feedback, and it's confirmed that he can take the pot and put it somewhere on the table, for example. And what the robot would then derive in a sort of a meta-reasoning step is that it generalizes and evaluates the strategy that he, as a robot, gave the pot, and the robot learned from this interaction that the human tends to use eye gaze in order to tell where something has to go. So this is just one of many possible iterations of co-construction, and the idea is really that this would basically go on over the years of joint collaboration and living in one household, so to speak. Now, luckily, we're not starting from scratch. So we have several achievements that we can build on. So one is that from the CRCEs, particularly of the area H for human, we have established already quite some work in a pipeline for the semantic annotation of human everyday activities and also models of human everyday activities. And second, we have, for the other direction, we have work on teaching and scaffolding that is done by Katharina and by Britta. So let me first walk you quickly through some achievements that we have and we can build on when we start out with the human to robot direction. So first of all, we have established jointly in Area H, we have established a human to robot pipeline, how we called it. And this basically provides us a way from human everyday activities to providing this as information to the robot. So it starts out by recording and collecting high volumes of multimodal data of human everyday activities. And we did this in the kitchen scenario. And just to give you an idea, so we have now about 100 participants who perform table settings in our biosignals lab. We did this for several different conditions, so the people have to arrange dinner table, breakfast table for 2 people, for 4 people, and so on. And we recorded the human behavior, and we recorded them in a synchronized way. We have brain activity, muscle activity, eye tracking. We have all these modalities captured by, for example, motion capturing, video, speech, and audio information. This has been recorded in the biosignals lab. We have, in addition, also asked the people to comment what they are doing. So we have concurrent think-alouds where people speak about how they perform these everyday activities. But we also have retrospective think-alouds where people comment on seeing themselves after carrying out the table setting. We have also, in collaboration with the neuroimaging lab from Manfred Herrmann, we have recorded first eye perspective information from the table setting, and we fed this into a video or a projector for a person lying in an MRI. And the person in the MRI perceives basically the table setting at doing it by him or herself, and we recorded the fMRT while they're watching people doing this. So that is basically mirror perception of a person doing table setting. And recently we also extended this to cover unexpected situations in a table setting, for example, if cups are falling or the table is cluttered or whatnot. So all of these data, or most of these data have been annotated in part manually, but mostly by automatic systems. And the idea is really to enable, for the full data set, have a structured activity models, and the structure is basically fed into what we call NEMs, or narrative-enabled episodic memories. So it's basically a memory of the robot of former episodes. And the way we are doing this, you can see here on the left, this is a person who is carrying out a table setting, and you can hear her commenting what she's doing. And you see here this kind of a partitur file. So we have speech, we have EEG, we have brain activity, muscle activity, and also we have down there we have the full annotation in terms of actions and tasks, what the people are doing. And from this, we can now automatically derive these annotations, at least in most of the cases, and we can go from these annotations to the NEMs. But more so, we recently established a common semantic format and an interface so that we can do a mass production of these NEMs. And the NEMs all end up in the NEM hub, so they are accessible to the robot and also queryable. So that means the robot can, at any time, can ask the NEM hub for retrieving information and episodes from former engagements. And then from these annotated data, we can learn and apply descriptive but also causal models of everyday activities. And here I just have a small selection of models that we built. So first of all, we built models from the speech recognition think-alouds, so we know exactly what people say when they do the everyday activities. We can derive from this, for example, semantic anchors. We also have multimodal action recognition from EMG and brain activity, so we know when a person is doing what, and we can access by this also more subtle and invisible hand movements, for example. We built up a multimodal activity recognition where we are applying convolutional neural networks and multiple multimodal data in order to come up from the subsymbolic level to the recognition. And we also have done, for example, attention shift recognition. So from brain activity and from gaze, we can tell when a person's attention is shifting from one object to another, for example. What we also recently have established that we can go all the way from a subsymbolic representation to a symbolic representation, and we are doing this by, from the bottom up, fusing information from multiple modalities, and from the top down, coming down with grammars of activities, and by using a generalized early parser, we can bring those two worlds together. That means we can basically bridge the gap from the subsymbolic representation on the human biosignal level to a structured information on what the person is doing. So this gives you a first idea on the achievements we have on the human to robot side when it comes to observing and learning. And now, as I said, this is a collaboration. Britta will talk about what we can do on the teaching and scaffolding side. Please.
Thank you. I'm trying to be quick. So the teaching and scaffolding is actually work that Katharina Rolfing and myself, we have done for quite some time now. And it's not about child-directed action demonstrations, but we have also looked at how do people actually also try to teach robots. And it turns out that they sometimes treat them really like children. And but before I start, just let me talk a little bit about this scaffolding thing. So what is scaffolding? It's a certain kind of teaching, and it means, of course, that the scaffolding is a way to support the learner to achieve a goal within her zone of proximal development that she couldn't achieve alone. So it means, so the zone of proximal development is that what you can reach by yourself. But sometimes the goal is lying outside. Actually, normally, most of the time it's outside. You cannot reach it. So you need a teacher who somehow moves the goal towards somewhere where you can reach it. And this is actually done by the teacher taking over those parts that the learner cannot yet achieve, which when you are interacting with a robot can be rather a lot. It depends on the robot, of course. And this allows also the learner to actually to free cognitive load because they don't have to think about how they get things done. It also entails that the teacher structures the task and provides sub-goals that are within the zone of proximal development. So again, this is something that is very important, that the teacher knows what the robot can achieve. And one goal is, so of course the goal is to reach the goal of the task, but the goal is of course also to increase the competence of the robot. That's really important. If the teacher doesn't want that, well, then things can fail actually easily. And this is what it's make really like a scaffold. It should be withdrawn gradually. So if you do it again and again, then the robot should learn more and more, and then the teacher should do less and less. Okay, so you withdraw it. Okay, and this of course requires you to have a model of the learner, and this is very difficult. I mean, if you have naive teachers who want to teach robots, they really have, in a way, a poor model of the robot, right? Because they don't understand what all these learning algorithms actually do. But that's really important in order to make learning proceed. So we have looked a little bit into scaffolding strategies. One of these is acoustic packaging. So when we look how parents talk to their children, they use a lot of scaffolding, and one of the scaffolding mechanisms they use is synchrony. And so it has been shown, for example, when you move an object and you label it at the same time, this apparently will enhance the learning of the label of the object in infants. And it can also be shown that there is indeed more low-level synchrony in child-directed interaction as compared to adult-directed interaction. So there are a lot of cues indicating that synchrony is really good for learning. And then there has been the idea of acoustic packaging. And the idea here was that the synchrony between language and events really help you to segment actions, because when you observe actions, it's really complicated. I mean, for us, it seems to be simple because we understand the actions. But imagine there are actions that you don't know yet, where you don't understand what the goal of it is, then it will be really difficult for you to understand where the action actually starts, because what is the means that brings about the goal state if you don't understand what the goal state actually is? And so if you're in such a situation, then it can help that somebody is speaking while performing this action. And even if as a child you may not be able to understand every word of that, you understand that when the speech starts and the speech ends, apparently this packages the action. And so this has been observed actually and shown in child-directed action that it works this way. See that in adult-adult interaction, this was actually just one task, like stacking cups into each other. And we saw that in adult-adult interaction, you just have 2 acoustic packages, but in adult-child interaction, for the same task, you have 4. And actually, we also looked at the robot, and we found even more, 6. This was because the robot was very, very slow, especially in the gaze. But we see that it's really more structured. And when we look at how many motions are actually within one acoustic package, we see that it's actually decreasing. So child-directed is here, and robot-directed even less. So we see that when humans want to teach a robot or a child, they really structure the actions more. And of course, you can use a lot of knowledge from an ontology, but these are low-level cues that even help you more. And if you have more of these cues, the less information you have and the less knowledge you have, the more you can gain from these. And so this is just one of the teaching and scaffolding things we have investigated. If we look at the other situation, when a robot wants to teach a human, again, we need to observe. The robot needs to observe what the human has understood, and we have seen actually there is already a lot of research being done here, that the human is being really observed and monitored and actually understood what is being done. And on the other hand, what is actually a good scaffolding strategy? And here again, in a different scenario, actually again in a kitchen. What we did was we used our robot, actually we used the simulation here, the robot Fluby, to explain to the user or to the participant actually different things. Informations actually turned out to work best when we didn't just explain any kind of information, but we told them where sweets were hidden. So this actually boosted a lot the motivation of the participants. And so in order to distract them, we let every now and then enter people the room to distract the participants or to get some noise out of loudspeakers. And that way we got them distracted. And we had a certain strategy then to scaffold them. And more specifically, we had actually even two strategies. So one state of the users or participants was not being engaged because they were distracted. Then we would just use a filled pause, like an or sometimes they were not understanding. This was actually the case, and even though it's really a simple, right? It's a simple task. You just have to listen and to remember the places, right, where things are being hidden. That's not very complicated, but still, it seemed to be difficult for some people to follow, especially when there was a distraction, and when there was a change of topic. So when you change from one place to another place, sometimes people weren't able to follow. And in this case, the robot was using a repetition. Again, very simple. And here again, the scaffolding strategy. So when the user was inattentive, then we have an adapted speech plan, and we have a speech synthesis that can actually produce hesitations, and the hesitations and silences were really going as long as you were inattentive. And so this way, we saw that actually the task performance in the situation with the scaffolding was significantly higher than without the scaffolding. Actually, just in the sweets condition, it wasn't so when the information seemed to be very boring. Nevertheless, we see here that scaffolding really is important. Actually, it also tells us something about the joint goals. If the participant doesn't accept the goal as a joint goal, it won't work. Okay, so we see here really low performance. And this actually led us to a joint project here. So we are now capable of using actually Tanya's lab here to investigate, because we don't know what's actually going on in the brain of the human participant when we are actually scaffolding him or her. And so now what we can do is we can have our robot in Bielefeld, and the robot can now interact with people sitting here in Bremen in the lab, and they can wear this cap so we can analyze brain signals and record them. And that is our goal, to understand how hesitations and other scaffolding strategies actually really can show up in the human signal. And then we might be able to better understand how we can scaffold human users in these situations. However, this lab is actually great because you can also do other studies and other things. So you have done here already a lot of human-human collaborations in augmented reality settings with people sitting elsewhere. So you can have lunch with somebody in another lab in another town, which is actually great. And once you have done that with Zoom, you probably will appreciate AR as a better means to do that. And I think this is really great, you can do actually a mapping of the human data, and so you have an immersive virtual environment, and you can explore the data. So all the data that has been recorded of human activities, you can visualize them in this AR, and you can walk through it, and you can see all the data you have recorded. And that allows us actually to have a better understanding of the data. So in order to really get towards a robots model of humans, I think we have seen, there's a typo here. We want to leverage human-robot and robot-human collaboration. And you have seen also there's a lot of decision-making going on here. This requires really models of decision making and, of course, cognitive models, especially for the metacognition capabilities here. And again, one of our goals here is really to reach some kind of co-construction. And we see that co-construction is actually a process that we currently do not see a lot in robotics. And I hope we can change this a little bit. And I think with all the work that has been done here within the EASE CRC, I think this is already really a great achievement. So having the ontology and having the CRAM architecture, which allows actually to incorporate human models in a deep way. And so I think we have a very good starting point here, and also the lab linking as a method really to collaborate over different towns. And so this is actually my last slide, and this is actually our final goal, to have a robot that we could interact with who really has an understanding of the human interaction partner and can thus really support us in our daily lives, and also allows to switch between learning and assisting, and so to have a more natural interaction with the robot. Thank you very much.
Yeah, thanks a lot, Britta. Thanks a lot, Hannah. I think that was very exciting and that I was hoping for as an answer to the challenge, right? Yeah, so it's now my distinct pleasure to introduce Giorgio. And Giorgio is now the scientific director of the Italian Institute of Technology, but in the community, Giorgio is known for being the motor behind the ICAP and kind of building the robot, building the software, and also kind of getting the YAP community. I think that's the second strongest community in the robotics we have. And Giorgio worked a lot in developmental robotics and had kind of an influential role in many of the European projects in the program. And yeah, so I think it fits very well to the talk we just had, and I think it gives the ICAP perspective to everything, right? Thanks a lot, Giorgio, for being here.
Thank you. Yeah, and a great introduction actually already tells what I'm going to present, because it's pretty much that. Actually, I have to, before I start, also acknowledge all the people that provided me with the material that I'm presenting today, because what I've done was to ask some of the researchers at IT to give me some of the latest results using the ICAP so that I could show them here. And unfortunately, I'm not doing research actively myself, because the institute is fairly large, and quite excitingly though, we also do other things that are not robotics, which are kind of fascinating. It's at a distance where you're not doing them all simultaneously, but just looking at them is very beautiful. I think it's one of the incredible aspects of science, of seeing how many things we could actually put together. Anyway, having said that, once upon a time there was a roboticist myself, but also there was a European project where we wanted to do humanoids. If you remember, and this was 2004, 2003, the European Commission put together this idea of larger projects called integrated projects. I think it was with FP6 for the first time that there was a chance to actually do something larger. And we thought, oh, why don't we do a full humanoid? This is one of the photos that is inspirational, comes from a movie, of course, but I think it represents well what we wanted to do, what we wanted to achieve. A robot that can do something, but also interact with people. So be, in a sense, a helper in various ways, both because it can talk to you or interact, and also then do some forceful action in the environment, not certainly carrying this much weight in our case. So the project was called RoboCub, and you see it was had the usual consortium, a number of partners, and one of the major goals of the project was actually to design human robot. In those times, there wasn't that much of ready-made available that you could purchase, apart from industrial robots, of course. Pretty much you had to design it yourself. This is the result. After 3.5 years, we had the robot built, and we call it the Formula One of the robots, but not because it's fast, but because it breaks after every competition, every experiment. In our case, the robot breaks, and we had to go there, fix things, typically cables. It was still a bit of a nightmare. You need to know how to fix the robot, because otherwise it's difficult to work with. On the other hand, it's a robot that has nice features, or at least something that we like, hands for enough manipulation, I would say. They're not perfect. In hindsight, they're too weak to actually, they're very sophisticated, but too weak to be capable of supporting proper manipulation, but they were enough to start with. In terms of sensors, I think we're happy with what we put together, and in particular, tactile sensors that we designed specifically for the iCub. We sort of modified the technology of capacitive sensing to be able to cover the entire body of the robot. The other important aspect, I believe, is that we made the entire project open source, tried to get people together. And I think in those times, I don't know these days, but it was quite cool that also the European Commission was supporting this community building activities, and there was I think it was a kind of a magic moment. It was a coordination action led by David Vernon, EU Cognition, that was also allowing the people that are here today to meet very often and discuss topics related to cognitive systems and applications to robotics. This just to show the hands, and of course the ball is empty because, as I say, the hand is not strong enough otherwise, but good enough for using stereo vision to reconstruct the shape of the object, planning reasonable grasp, and lifting the object. This is a bit better type of skill. Some of the work that we've done to develop force control on the iCub and on a complicated task like this one, where the robot can be disturbed, and both tactile sensors and force torque sensors that are embedded into the robot's body allow measuring external contact forces and generating this type of behaviors. I mentioned, last but not least, the project's open source, and surprisingly, there are still requests for copies of the iCub to research. So I think by the end of the year, there's going to be about 50 robots done. And the robot is super expensive, well, relatively super expensive. It's about 250,000 euros. Therefore, it's kind of, in a sense, incredible that there are still people that are developing some research on the iCub. I must say there's, these days, I guess there's a lot, I think we ended up in a niche that is kind of interesting because most people are working on human-robot interaction using the iCub, and I think it's kind of, the robot allows itself to be used in that case very, very effectively, and this is exactly what I'm going to describe in a moment. This is a setup, one of the research lines at the Institute, where they're using cognitive neuroscience methods to study the human side of human-robot interaction. So it's it's not the robotics side very much, although they're reusing some of the development that happened on the robot. So controlling, reaching, and grasping, since it's already done, can be used in experiments in various ways. Let me start with the first experiment. It's kind of a simple one, or if you like, a pilot experiment. It's Posner queuing. This goes like this, basically. In the original Posner queuing, there were arrows, there was a stimulus appearing either on the same side of the arrow on the opposite side. The same side is called the valid queue, the opposite side is the invalid queue. And if you measure, for instance, reaction times, you discover there's a difference. So the arrow will tell you, in a sense, where to look, and therefore you're faster in that case. If the stimulus appears on the other side, you're slower. And you can measure these times, and we say it appears to check whether this is also influential. And also because in that moment, the robot moves the eyes. And the idea is that if there's a difference there, it means there's something happening in between. Your brain may be doing some processing, and if there's a difference, means that in the future, when we're thinking of robots that are interacting with us, we have to be very precise with the timing, because otherwise we may not get an effect. So this is the experiment. The eye contact, that's simple. I mean, these days, identifying face and eyes from robots' cameras is relatively okay. And then, as you see, there are the two cases. The robot looks in one direction, the stimulus appears opposite, and so forth. The no eye contact is also easy enough. The robot looks down, so it's not looking in your eyes, and then looks or doesn't look at the stimulus. Okay, this is one result. In a sense, as expected, or don't know whether it's expected, but anyway, this is the result. If the robot looks at you, there's an effect. If the robot doesn't look at you, there's no effect. And we say, oh, wow, this means that the mutual gaze is important. It's a cool effect, and we were very happy until we started manipulating the SOA, so the moment from when the robot starts moving, let's say, and the moment the stimulus appears. And it changes. So, I mean, the experiment remains cool, but it's interesting to note that a difference in timing generates a difference in robots' perception. Therefore, again, maybe for the robots of the future, they need to be very accurate when interacting with us, because they can generate completely different, let's say, we can perceive them in a completely different way depending on a slight modification in time. So this is to summarize the first experiment. The joint attention is modulated by these, what we call strategic top-down components, which means the longer time means perhaps that the brain has more time to process what it's seeing, and therefore there's a different type of result with respect to the reaction times. It's not only reaction times, we also use the EEG. I haven't showed the results, but you can also see in the EEG a difference in the two cases, so this is confirmed. And also, as a general conclusion, of course, the robot's gaze is treated as a social signal, which is not to be given for granted. I mean, it's a robot, and it's two cameras. They look kind of human enough, but they certainly are not a person. Another experiment, again, and this I think bears a lesson for the design of robots to be used later in different practical applications. And here we had a game, and the game is made as follows. You subject control a little car that is going against another car controlled by the robot. You can decide whether to go straight and take the risk of crashing with the robot's car or deviate. And depending on whether you stay or deviate, there's a point matrix, and of course your goal is to maximize your score. And if you crash, there's a -4. Of course, if you deviate, if the other person deviates, or if the robot deviates and you stay, you get a number of points. If you both deviate, so you and the robot, there's less points. So of course, if you want to maximize, you have to take some risk. And of course, we measure what happens. Also in this case, wanted to measure what happens when the robot looks at you. So in case of mutual gaze, is it the robot, what? Is it influencing your decision making or perhaps not? This is the video. By the way, there are also the names of the authors, the PI, Agnieszka Wikowska, who's doing this as part of an ERC grant. And so you see a bit here what happens. Wanted just to show you the screen where the game is happening. The robot is actually pressing a real button, although everything is later electronically controlled. And you see the game happens there. There's a moment of decision. You actually don't see, the screen goes blank for a moment. You have to take a decision, and then the game continues. Okay, what happens? There are, sorry, I forgot to tell you that there are, let's say, robots behaving in certain runs are behaving with different amount of mutual versus averted gaze. So 70% versus 30% in the two cases, just to compare whether there's a percentage that influences differently the performance, but nothing happens, or everything goes well in this case, and there's a difference indeed between the two conditions. So the robot is influencing your response time when you're taking a decision, and this is already bad in a sense, because the robot looks at you and you slower. So there's something happening, and this something is already tricky. So would you like to put a social robot in a factory floor? Maybe a robot that looks at you? I don't know. Maybe if you have to be focused on a task, you don't want a social robot there. There are other situations where a social robot may be more effective, but certainly not this one. This is also confirmed from EEG. This is the t-values. The plots shows t-values of differences in the averted versus mutual gaze. And you see, this is at least what our neuroscientists told me, that there's a higher synchronization during mutual gaze in a specific frequency band called the alpha band. And this means that it's let's say, a hallmark of the brain doing a processing of this social signal, which is the processing is for suppressing the robot's gaze during the eye contact. So this is exactly why you get activated, you become slower, and we see that you also take different decisions. This is another plot that shows how much of the optimal strategy you are applying depending on the conditions. And the one thing that is that you see from this plot is that there's the more the robot is looking at you, the less you are applying the optimal strategy. The optimal strategy is the one to the left, is called win, stay, lose, shift. Basically, if you win, you keep repeating the same action, you shift in case you lose. And this is actually, without knowing, is the optimal strategy that is used by the robot. The robot is using exactly this strategy. The participants don't know that, but implicitly they're using the optimal strategy more often in cases where the gaze is averted. We tried all other strategies that are possible, and there's no effect there. The effect is only visible for the optimal strategy. Okay, let me wrap up. So again, the robot gaze is a very strong social signal. It's influencing performance. Therefore, I mean, the question is whether you want to have a robot gaze in cases where you actually have to focus on a specific task. Or maybe in those cases, it's better to have no robot gaze, or a standard industrial robotics may be better. So this is, I wanted to conclude with another experiment. I'll be very fast, 5 minutes and I'm done, or maybe less. This is an application of some of these studies, of course not exactly the same, to program, a training program for kids diagnosed with autistic spectrum disorders. And the thing we done was, well, there was a pilot using a toy robot that is called Cosmo. I don't know if you heard of it. A little mobile car that can be programmed to do certain things. It's very cute and can be used for that, but it's not very effective for complicated behaviors. We done another experiment, and this is a bit more complicated. This was basically the scenario. The robot interacting with a kid. There's a therapist always present there and sort of guiding the game, and the robot was trying to teach perspective taking to the kids. And this is something that can be taught, and it actually improves quality of life in the long term, because it's one of the skills that is missing in children diagnosed with autistic spectrum disorders. So this was the, say, construction of the setup. The game is very simple. There are cubes with different faces that can be shown either from, of course, the robot can show them and ask them, what is the question we're asking the kids is, what is the face that is seen by the robot? So trying to ask them to put in the robot's shoes, so to speak, and answer to these questions, and of course, getting feedback from the robot itself. So this is a video. Of course, it's a fake, because we could show the kids participating in the experiments. These are, our kids, and we filmed the experiment for the sake of explaining how it works, and the robot is providing feedback, no, things didn't go well, or showing, 2 thumbs up, things are going well. So the experiment, by the way, you see that the kid and the therapists are wearing masks. This happened during COVID, which was a nightmare, considering that the experiment ran for 9 months, super complicated procedures. But anyway, the important part is that there were results. These are standardized tests that are typically delivered to assess the capabilities of the kids and rank them on different scales. And what we've done, we checked pre and post training with the robot. We did all counterbalance groups or children in such a way that all of them eventually will get the training, but we could compare for periods of time whether they had the training or not, and check the differences. And what is shown here is that for 2 of these tests, like the geometric puzzles, so composing simple puzzles, and the theory of mind test, there's a difference, there's improvement by using the robot, which is, I think it's interesting. It's only one run that we managed to do, but I think in the continuation in what we can do next sounds like quite an impressive result. So this is basically summarizing, take-home message. There's something that can be done with social robots. There is certainly not necessarily having them in a factory floor, but maybe in this type of applications. People that contributed to the ICAP, this is a picture from a few years ago. As you can imagine, designing the robot and running all these different experiments required many, many people. And this is the group doing the experiments with the human-robot interaction. That is one of the research lines at the Institute. Thank you.
Thanks. So I think we are ready for a coffee break, right? I think so. Enjoy your coffee, and we will then have our final session today. final session for the day with talks, and it's my particular pleasure to welcome Markus Winze. And Markus has again been in the European robotics community with the topic of cognitive vision from the very beginning, and I think if we have in the community one researcher, I think, who is essentially kind of at the intersection of robot vision and cognitive vision, I think it's Markus, and who is always pushing that vision is not kind of vision, but it has to be brought to robots to actually make a difference in the world, right? And yeah, so it's my pleasure to kind of welcome you here, and I'm looking forward to your talk. Thanks.
Thank you very much, Michael, for the very nice and on-the-point introduction. I will try a bit different today. It's not just an overview of some of the stories we did, but it's also going back to really see and discuss what is missing, what did we learn, and I hope a few more youngsters are coming, because some points are directly addressed to them for future research. So again, big thanks, like Giorgio before. I think it's always a team that provides all the input. So yeah, I'm really happy to have great students, because that's really necessary. And at the end of the talk, there's never time for that, to do it in full words, but just go away. So as the title said, finally, we are moving to what everybody ever thought the robot should do: cleaning the table, getting the glasses off. We are not getting the glasses off yet, but we are really moving toward transparent objects for a medical project. So I'll show you the progress towards that and what we learned all the way to get there. And I really want to use that to rethink a bit what is robotics, because that's a robotics lab. And we are also playing in the computer vision community, and it's very different. So I'm really going back and saying what is our experience, what we see as difficulties, and maybe provoke some thoughts, or present first ideas what can be done. First in lessons learned, 3 slides, and then what's next. I think robotic tasks are just the most important thing to consider. So for those who don't know me, I can be very quick, because basically I've nearly seen everyone in here and personally talked to. So we do everything. So we try to make robots see, and we do everything with objects. So we want to model objects, recognize objects, classify them, finally do the pose estimation and grasp objects, and then manipulate them, so putting them down somewhere and placing the objects again. And of course that involves some scene understanding form and function, and we do whatever we have. So we worked a lot with stereo vision, and then moved to the Kinect and RealSense depth cameras, because just they provided a lot of very useful information directly. And just to set you in the right mood, some of the examples we had. So we had a robot that was helping elderly people at home, and that's a proud grandpa, and the nephew took the video and allowed us to show it. They said, please pick that up, because that's, danger of falling, and old people shouldn't do that. And it's completely vision operated. So we see what is on the plane, we extract the plane, we see what sticks out of the plane, we extract grasp points. We actually lift it, look back on the floor and see if it's gone. If it's gone, we put it in the basket. If it's not gone, we see that it's still there, and we would retry. So there's no tactile feedback in the grip or nothing, because it's just a 16,000 robot, mobile robot with an arm that we built, and it was really, really useful and very helpful. That project ended 6 years ago. We have data from more than a year of in homes with older adults. We're still using the data and find new evidence for things that we are looking for, because we have so much data. I mean, the robots were just running there, and we recorded, logged everything they ever did, just to learn what people would do with a robot at home. And that's another one. Aeolus Robotics is maybe not that well known. It's a Taiwanese company. They set out 6 years ago, after the end of the other project, and came to us and said, oh yeah, we want to build a tidy up robot farm for the homes, which is like my vision. and they said, oh, Taiwanese, oh, we built the hardware. 1 year and we have the robot. So this is like 4 or 5 years later. It's still not tidying up in a room, but you see that we can do quite some nice things. So we cannot grasp it because it's just, the object is just too wide, so we have to push it towards the corner and do that, and avoid the obstacles and so on. So there's some really nice progress, and you can do it with many different objects. I think even books and so on. So that's really good. And the company has now a big base actually in Vienna. So I'm a roboticist that said we need to move vision into robotics, and I strongly, very, very strongly believe in models. I mean, of course, I can speak to Michael always because he also believes in models. So robots move around. The first thing they need to do is detect floor for safe navigation, and a robot should always use that information. So we always do that because once you have the floor, everything else becomes a piece of cake. I mean, it's much easier than just having an image and finding a chair if you have that context, because that's the floor, and that the board of the floor is maybe the chair, and the desk and the wall, but it's so much simpler. And of course, if you have the 3D information, it's again yet simpler. And that goes on, because once I know the floor, I know the horizontals, I find horizontal planes, and on the planes I find the objects. And I show you again and again that, you know, this just simplifies all our vision problems that otherwise we have. But I need to go to the robotic tasks, because I believe it comes always, the task is the first thing that then tunes my methods. And I strongly claim that everything I've ever seen can be put into these 3 categories. So either the robot sets out to search an object, which implies that it knows something about the object, models again. I can't look for my mark if I've never seen my mark, and I can't look for a mark, even a class of, if I've never seen a mark or learned anything about the mark before. So it makes no sense to do search without knowledge. And you're in an environment that you also are not exploring every time again, because that would be outright stupid. But of course, you visit the places first where you saw the objects the last time, or you believe, have some belief it's going to be there. Another task set is just clear, which means tidy up, or just make order, or whatever, anything in that direction. So it includes the grasping now, and of course object placing, which is much too little studied, and you need all the 3D information about the objects, and I will talk about that, what we are doing. And I think assembly is just a variation actually of clear, because it just has more rigid constraints. I mean, you need to fit parts, and you might have more order to start initially, but otherwise it's more or less the same task. In other words, what you extract from that is there are some very clear tasks that you give to the robot. So first you need to detect something, then you want to grasp it, and then you want to place it. And I claim under this falls everything, and I will shortly show you, coming from the vision side, what we did so far. A few success stories before I end up at the lessons learned. So for tidy up, our niche system should have. And then once I know my environment and I have a specific sensor like a Kinect, and there's data beyond 2 meters is more or less useless, you can find out how to cover all the areas and so on. And then again, we are using a lot the context. So if I want to tidy up that region, so first of all, which region? Point me at the tables, or structure the environment so I have local areas that I can do, not the entire room at one, because that's much too much. I can only do local. So we do semantic segmentation locally, which is very noisy, but then we use the plane hypothesis because we have them and we can employ them again, and plane extraction is actually really easy, and you have quite a lot of data for planes, so it's very robust. And then you use local verification of all the objects on top, and you see that we are very, very close to ground truth. You could still go then close and grasp the objects, and that's going to be the next step. And there's going to be many, many methods. First, there is many ways to learn the grasps. I mean, totally directly from the RGB image, from the shape, which is basically the depth information and the shape affordance you're using, improving over, using every experience and so on. Or you could split it in 2, which is pose estimation and then do the planning. We tried both, and I will later show you what is the best, or what we learned so far, what is the best and working best for us. Just an example. So that's completely depth-based. We don't know anything on the objects. Remember, that was the glove in the very first video of the grandpa at home. That's basically the method we used. Pick up everything that you can grasp, which basically fits into your hand. And it's a very old learning method, which is just depth-based binary features. So Viola Jones method basically on depth. And it's really powerful. It separates objects in a heap, which is then much easier to recognize. So if you don't recognize them in the heap, you will recognize them individually. And we need to wait a bit more because you then really see that, yes, it's always very, it looks like superb that it's really taking only one object, but it doesn't know anything about objects. So here you will see that exactly. It just, you know, it was a good grasp, it picked up two, but still it makes sense to pick this up and separate it from the other objects. And you can then go and try other methods. So one is here coming from all the grasps we have annotated on objects, and whatever object grasp was tried, we remember it if it was successful or not successful, and try to keep learning from that. It's a bit expensive, but sometimes it helps to pick out the more robust ones. So actually with, so that's with the HSR robot from Toyota. So actually the handle is okay, but only for some marks that are not too heavy. So if you have a heavy porcelain, it's not going to work. And you can relearn, and that's what we do, and that's the platform we use at the moment. I see Mark is here, so Mark, platform is very robust. That's what we really love. I mean, that's good. The gripper could be better. But that's for the next version. Okay, so that was the grasping, but we do a lot of vision work. And to extend the database, you need to have many objects. And ideally, in my opinion, we should learn from the models that we have. CAD models, any other models that we obtain from the, looking at objects, and we should learn from that. And I have a PhD student, actually a few of them, and they tried to do that only from simulation. And that worked very well. Astonishingly well. You need to do a few things to make it run, but it's relatively easy. What we particularly learned, you need to render images for learning that include the domain objects, because as closer you are at the target domain, the easier it's going to be. What we also learned, it's very good to have multi-scale features, because they better capture this local to global object information and better handle occlusion, which you always have. And then, of course, you need to evaluate on a data set, because otherwise you can't compare that, particularly not in the computer vision community, but also in robotics, you kind of need a data set. And these data sets always look horrible. I mean, for a human eye, this is really confusing what is shown here. But actually, these images are really easy for computer vision, because they have tons of texture on the background, which is very easily just discarded. So these images are much better and easier actually for computer vision than the normal ones, and I'll show you later on some of the things we did from the robot. And just to highlight one more method that we have, I had another excellent PhD student, and he really wanted to go for all these data sets. So there's the benchmark on object pose estimation called BOP. Thomas Hodan from Prague is established that, and in the vision community it's huge. There's like 15 data sets in this big benchmark, and you can test against it. And I had a PhD student, he really wanted to go to ICCV because it's in his hometown in Seoul. I mean, he basically wanted a trip home, and for that get ICCV. And ICCV is in the vision community, basically that's the top conference, that's the best you can do. So we had a year and said, okay, how do we do that? I mean, basically we need to beat the benchmark. I mean, in computer vision, it's really that easy. There's no other task, beat the benchmark. So we analyzed the benchmarks and we found two things. None of the methods explicitly handles occlusion. They just try to go over it, but not explicitly say, you know, I know actually from my annotations that this must be occluded. It's not otherwise possible. And the second thing was symmetry. So we did some occlusion handling here that we explicitly said, you know, there must be some occlusion, please explicitly handle that. And the second thing is we got rid of this stupid notion that, I mean, if you annotate this object, this is two parts that would handle that case actually. So I don't think it's the best solution, but it was a solution. And the thing worked. So we beat kind of many of these part BOP challenges. There's one T less, which is another one that's really difficult because we are now at 30%. But textureless objects is anyway nothing the vision community would love, because that's really always the hard case. What is more interesting for me is we won the two challenges that are most related to robotics. So that's the YCB video object challenge, you know, the Yale Carnegie Berkeley data set, and that's the Rutgers Amazon picking challenge. So we're still, I mean, that was 3 years ago, so we are not the best yet, but we're still one of the top methods. And then we put everything that we had on our robot and run it in our lab. So it's kind of the same objects that we learned already. It's nothing new. I mean, there's like standard data set of 51 objects and so on. And we created images like that in our kitchen. And we tried to compare that to, you know, performance on images taken by humans of these scenes and then images taken from the robot. And not a surprising finding, but I had the data now, is performance drop 40 to 50%. I mean, basically you're now 40%, 50% guessing what it is. And it was consistent. I mean, we split up the database in different room sections that we have taken and so on. It didn't matter. It was always the same situation. And the problem is that whatever you learn from just gives a bias. And the robot is not selecting any views. So whenever a human is selecting a view, there's a human bias. So you center the object, you have reasonable image size and so on. So the robot doesn't do that. We don't have yet the procedure for the for the robot to make actually good images. So the viewpoint, the object size, occlusion, clutter in particular were difficult. So you really need to use this context. So we said, okay, good, let's investigate what's wrong here. And one of the first lessons we learned is, so of course, whatever is annotated is going to be learned, nothing else. And then we found out that in some of the data sets where we are at like 80%, it seems like the methods are not getting any better. It's like 81, 81 and a half. And then we looked at the data set and we found out this is the problem. The problem is that the data sets are annotated from the first person perspective, but you have depth. So yes, you overlay the 3D model of the object, but you haven't seen the scene from the side. And if you see it from the side, this is what happens, because from the front it looks good, but from the side it looks actually bad. And we believe strongly that for several of the data set, that's the issue. So we will never get actually very good pose results, because that's just basically impossible, because ground truth actually needs to be challenged. So it's always the question, do you tune the architecture or do you want to solve a problem? So my colleague said, okay, we have a robot task, we want to do it, let's do it right. Let's try to make a data set that has just the best pose we can do, and it will never be perfect, because we it's basically impossible to get the ground truth on where this object is really lying, but let's have all views. So we took the setup our control engineers had, a floor down, with this nice cooker hanging on the floor, on the ceiling, and just created, we have markers on the as reference around the objects, like you saw in the others, just to make sure that the robot inaccuracies are also compensated for. And we go around, we take 100 and few views per scene with 2 real-sense sensors, and we get quasi very, very excellent views from all sides. And then a colleague made a nice tool so that you have several views, always orthogonal, low down, low up, at the same time on your screen. And one time you move the object 3D, it takes some time actually even for humans to really move it there. We have some additional methods for fitting to the depth data, fitting to the plane actually, because we have the models of the object. So we try to do that because we know that is a constraint. And then we look like at all the images. And if you have that from the one object, I mean, yes, it takes a bit more time, But the nice thing is you have it immediately for all the 104 images because that's all set. So we have tons of data now. Another really nice thing is if you take a photo neo laser sensor, which is a very accurate sensor from a company in Bratislava, and you paint this transparent object, you get a very good model of that object. And that is helping us a lot because we have again and again companies coming to us asking, you know, can you find that object? And they give us object models. And then we learn, oh God, these object models are, I don't know, old version, never correct. I mean, you know, it's 2 millimeters larger or smaller. And, you know, that for the depths, that means quite a lot. So we get very accurate models and can use them then again. So if we have the model, we can put the transparent object in the scene because visually we see it. I mean, yes, the depth data is not going to see it, but visually we see it. And then you can create many, many scenes as your count rules, and please don't look too long at that because I think you get just dizzy. And then we go back to the image methods and say, oh my God, so depth is now pretty much useless. I go back to color images and try to learn artificially what I should see and use only the color channel to do that. And then Stefan just combined two very clever methods in a one end-to-end trainable. So we separated it to learn geometric correspondences and then do the pose estimation from that. And turns out, yes, we are yet again 5% better than the methods before. And the nice thing he additionally did, he tinkered around with all these hyperparameters, and he can do now all the objects in parallel rather than doing them sequentially, which just speeds up the method. So you get up to like 90 objects in 24 frames per second. That's the problem with the transparent objects if you use the depths. So you see the scene from the side then. I mean, basically you have some artifacts, nothing else. So we're really back to RGB. And that's what you see when you learn. You see that you have quite some deviation of object hypotheses. And what we do here is single object grasping is fine. I basically say this is solved. As long as a single object is in your scene on a plane, we can do that, including transparent objects. It's robust enough. But we have problems if there's clutter or different background. Again, the checkerboard is only there for reference for us. So these methods sometimes fail, in particularly if you have occlusion or objects standing next to each other and there's part occlusion, there's interreflections, whatever. I mean, there's always some issues. And what we find works best is the good old computer vision method of hypothesis and verify. Because there's tons of stuff you know. You can reproject the model and you can use physics, which basically, you know, the pure computer vision method doesn't do. It just recognizes an object and creates actually a hypothesis. Yeah, possibly there's the object. So you can do one thing if you have depth data, you know, go back. I mean, every learning-based method, you know, creates a vector of features and then finds like, oh, that's it. But now you can go back with the model and say, okay, is it? Can I confirm that? It's a bit expensive to do and doesn't work for everything, but it's pretty reasonable. Even more sense makes physics simulation additionally, and I think one of the best things to show is the video. So we extract the plane, and we know that objects should stand stably on the plane, and they should not intersect with each other. And then we go basically through all the hypotheses that have been created and look what is best. So for example, now the handle showed up because that explains even more data points. And you see that we can reasonably explain a scene that is quite nice and complex and closer looks like what might happen in my kitchen with, I think, the exception of that object in the background, which we never detect, but I think for a start, that's pretty good. And the same thing can be done with visual objects. So again, you have multiple hypotheses. I can just use them, refine them for whatever pose I have the object in. You see here that there's quite some different hypotheses that come up. And that's the way how it's done. So first you refine by reprojecting, and then you use the plane coordinates because the plane is so easy to extract, and just make sure that it stably stands on the surface. And that can be done for different poses. Yeah, here it is. Here's the animation. And we get relatively accurate pose hypothesis that can then be grasped for transparent objects only from the RGB image. Okay, so the second lessons learned is knowledge. Nothing new here. I don't think I have to speak long about that because, yeah, I mean, all this event is about using this in robotics. So every bit of context, in my opinion, that you can build into your system to robustify it is just very useful. And we learned this, what the nice thing of this approach with this hypothesis and verify is that whenever in the vision community someone proposes like a new YOLO or a new whatever, we can take their hypothesis creator, and if the hypotheses are better than the ones we got before, the last step of the verification will be easier or even much better again. Yeah? So it's a very nice thing of exploiting actually what others might provide. So yeah, models and memory are essential. And I hope we can really slowly move from single demos, robot demos with single standing objects to a bit more complex scenarios. The next one is on robot systems. So yes, we have data sets, but the world is richer than the data set, definitely. And if you have a data set and how to do this end-to-end learning, the question is always how to transfer it to another robot. Besides the fact that you create a hypothesis, so can I tell from the hypothesis what went wrong and why it went wrong? So I think you need these intermediate steps, for example, the pose estimation, you need to know which objects you are, and of course I would really like to talk to my system and find out why it doesn't work. We had a very nice presentation in Vienna where we showed like our pose estimation system, and you know, whenever we made experiments with the robot grasping something in a more complex scene, and then the robot would explain why it went wrong. And sometimes the explanations were like really bad, and sometimes like it was the real thing that was more or less going on. And we asked users, which robots would they trust more? The answer was obvious, you know, those that could explain what went wrong and then, you know, just like redid it. And for this to make it run, you need many, many things. So we would love to have a reasoning system. We would love to have the verbal system that you just presented before. So I really think one of the real missing thing is the orchestration of all these robot capabilities. So I highly love reuse. And I think reuse should be really done by evaluating tasks. So my last point here is robotics sets out to solve tasks and not provides just methods. And I strongly believe actually we should not even evaluate robot A with method B on a specific thing, but we should only test a task A and a task B. And I don't care which robot actually is going to solve it and which method is solving, but I would like to know that there's progress on the task. If you want to know why I'm concluding that, I have been at the IROS in Macau, and I think I saw a day-long novel approaches on a blocks world of colored blocks and stacking them. And I remember I did that when I was a student. And I thought something is wrong here. You know, I mean, yes, it's a new method and maybe it has potential, but unless you show me that it has potential beyond what I did 20 years ago, I'm not really believing you. So sorry, just a few slides on a proposal. So we have this Burg benchmark for understanding object grasping. It's on GitHub. I guess if you search GitHub and Burg and benchmark and grasping, it's sufficient. You only define the task. We extend a bit the grasper challenge where you have these boards that you can put things back, because placing, I think, is totally understudied. That would be really cool. And yeah, you know, you can have any level of complexity you want, not any, but we can do pretty much with our vision system right now. Thanks. Following, I have missed the talk of Michael, but I think I know that evaluation of the tasks, I think, is the way to go. And I would love to share the tools like Michael always proposes to enable the community. Thank you.
don't have discussion afterwards because we kind of are tough in the time, and we have the discussions afterwards, right? So, yeah. So now it's my pleasure to introduce Karin. Karin is yet another former student, and she was also a member of the, or actually is of the East Research Center. And yeah, Karin did her PhD in Munich, and she is now professor in Chalmers, and her specialty is interpreting human activities, semantic interpretation, and semantic robot programming. And yeah, we are looking forward to your presentation, and thanks for being here.
Thank you, Mike. We have this microphone? Okay. Good, thank you. I don't know if the slides will be shown now, perhaps. It is always wonderful working on Linux, right? You never know if the presentation will work or not. Okay, so thank you, Michael, for a nice introduction. Yeah, I feel like at home, very nice, familiar faces. Thank you all for being here and for the invitation. So today I will talk about what we've been doing the last couple of years, and it's mostly related to failures, because as we heard from the previous talks, robots will fail, right? Okay, so this is not working. Yes. Okay, so the main task is household scenarios, and of course we want to see how can we enable these models so that they also work in a different industrial scenario. So how can we transfer knowledge? And more importantly, can we, the designers, know what is the agent learning? What is actually the model that is being learned, right? So the outline of presentation is very brief. So I will present the challenges that we're currently working on our lab, and I think intersect with the things is also working on. The current work we have on some of the outlook that we are working on. So the first challenge, of course, we have this scenario, right? So the robot has in front of his 2 pots, and it knows that the general concept is in its good pasta, right? And then the question is, okay, what should I do? What is the first problem is we need to learn and we need to recognize the tasks that need to be done, right? The next one is to extract the semantic representation. So, and this is important because then robots will be able to see, have I seen something similar before? Can I reuse experience that I have before? And that's why semantics is important. Then we have challenge 3 and 4, which is basically automatically collecting these experiences, which is similar to what the NIMS are doing now it is. And the challenge 4 is basically anticipate and prevent errors or failures at different levels of the execution or the recognition. For example, in this case, he has the robot has 2 different pots, and the task is to pour, of course, the tomato sauce. Which of the pots should be used? The small one, the big one? What will happen if it's doing it in the small one? Will it be better to do it in the big one? And finally, we have the execution. So this is some of the main challenges that we're working on right now. And we have been addressing the first part, so this is something I did already on my PhD. So we have the signals, and then we interpret the activities. And the more important part is that it's human-readable activities. So it's like grasping, pouring, putting something somewhere. And the next step is, okay, once we have the plan, or we can have like a task plan, and choose one task that robot needs to execute, there are different possibilities for executing this task, right? So on one hand, if we see the example of the cooking pasta, he has 2 different pots. And he can recognize in the memory that, okay, if I use the bigger one, I will have higher success chances, right? But if I use the smaller one, most probably I will have a failure, and that will lead to another problem, right, which is the tomato sauce on the floor, and that will lead to a worse consequence if I don't clean that, right? So, and then finally, once we detected the correct, let's say, parameters, like the correct size of the pot and all these high-level parameters, how can we then put that back to the robot, so in a robot planning system? And finally, execution. What are we doing for addressing these challenges? So The main key is that we want the robot to extract from the demonstrations or from videos or from different sources of information 3 components. What is the task that needs to be executed? How is the task that needs to be executed, and why? And this leads to the explainability, and this is basically extracting the purpose. For that, as I mentioned before, we're working on how to extract this automatically from the demonstrations, which is basically continuous data that we obtain and using first-order logic prologue to, with a decision tree to actually detect the higher-level representations. From here, I have a small video how it works. Yes. So this we have a virtual environment. Of course, we obtain information from this virtual environment. This was a very nice collaboration with Professor Inamura from Japan. And if you see here, the task is basically doing the dishes. And how many different ways do you think we have for doing the dishes? A lot. And here, you see that automatically the system is detecting each of the steps, the high-level steps, like grasping or getting the sponge, putting it on the plate, etc. And that is what is going to be generated here. We call it the task graph. Then we have, of course, a lot of different participants. We have around 11 participants just to assess how different the same task is being executed by different participants. Of course, everybody has a different style. Everybody has different repetitions. But if we combine everything into a single graph representation, we can observe main patterns, right? And this is the important part. At some point, you will see blue dots on the floor, on the part there. Yes, and that represents the main task for, let's say, washing the dishes. Then we're using that as a planning for the robot to execute the tasks. And at that time, that's a work I did in Munich. We have, of course, the PR2. And then here, the robot is now executing. And the most important part, if you remember from the virtual reality, we didn't have cups. We only have plates, and we only have forks, I think. So because of the ontology we have on top, the robot is able to generalize to new objects on the scene. And if you saw the red parts at the end of the robot, it's because the robot is recognizing his own movements online, right? So this is good because then the robot at some point will detect something got wrong, right? Now, what about, what we started doing is, okay, now we have the plan. What about if we put it into a planner? What will happen, right? And this is the next work we have. So we have the demonstrations. We started with a very small problem, right? Stacking cubes, how complicated that will be. So surprise, everybody has different styles as well. So here we are automatically segmenting everything the human is doing. And from these segmentations, we are automatically correcting operators. These operators are going to be used for generating the domain in a PDDL planner, for example. And yes, and those will be automatically collected from the demonstrations. And of course, we can see that there are a lot of different operators. And with this one, we can actually automatically generate the domain and the goal into a planning domain. So we no longer have to engineer that, right? And then we give the goal, and we give a new goal. And this is what's surprising, because there are some movements we didn't teach to the robot, and still the planner was able to optimize that, right, for achieving the task. So that was a very nice work. This is the work of my PhD student, and it was a very nice collaboration with NVIDIA. And then we say, okay, of course we had a lot of errors, and we had a lot of problems. And we say, okay, hold on. What about if at some point something happened? Can we actually recognize that something went wrong? And how can we actually correct it? And if we can predict it, prevent it, right? So then we say, okay, we have this pipeline. So we have the demonstration, then we have the task, all these actions. And then we say, okay, let's use a verification tool, we call it. And then we say, okay, let's give some responsibility to the user, right? The user should be able to detect errors, right? At the execution. So we have the plan, and this plan was sent to simulator. The user was able to see it either using HoloLens or a tablet or using ARVIS. And once the user was satisfied, it was sent it back to the execution. And this is what happened. So this is I think this is a HoloLens, this is a tablet, and the last one is ARVIS, which is basically the simulator we use in robotics, right? And this is how it looks like. This was a very nice collaboration also in Japan. I don't know if you see something here different. I don't know if you were able to see the errors, but all these videos actually present errors. So we realize, for us, for humans, it's very, very difficult to see these errors. We focus on the wrong part of the error, right? Because we are, especially if we expect non-experts to actually detect errors, right? So then we say, okay, nevertheless, which will be the platform that is being, used by users? So we have a study, and then we say, okay, HoloLens, we use HoloLens 1, which is heavy, and that was not the favorite one. And then we have the tablet or Arbis, those were the preferred ones. Nowadays we have HoloLens 2 and want to do the next study. But this was very interesting for us because they indicates that users were not able to detect 100% errors. Then we cannot leave the responsibility to the users, right? Then we say, okay, what happens if we replace this of the users by actually the robot having more responsibility, right? So now the robot at some point, once the plan is being executed or being sent to the robot, and now it's an execution phase, the robot is able to detect, hey, something is wrong, or if the robot already failed, is able to explain what went wrong, right? Like if I put it too high or I drop it too fast or something like that. So for that, we started working on this action failure detection, and we're using causal models. What is the main problem of causal models? I like this video. I like this picture. I mean, everything is sent here, right? Is it really the cat causing that? Probably not. And this is one problem, because the things we observe are not necessarily the things that are actually causing what is the consequence, right? So we started with it's the same scenario, and then we have analyzed only stacking one cube. We have this set of random variables, and we're using the Bayesian network to create a causal model. And then we, on purpose, we put some variables that we know they don't have any connection, and the model captured those. We also have the estimation of the parameters, so we want to see how much of the information that we obtain from simulations we can actually use on reality. And this is what happened. So this is the this is the theta value, the parameter estimation that we obtain from simulations. And then we just analyze a small set of that into the real robot. The interesting part is, if you see here, everything is more or less good. This is representing, the different colors represent the success or the failure, depending on the area. This, imagine there is too much to the right, too much to the left, too high, too small, etc. And as you saw in the video, that was a transfer. How much can we actually transfer? So we have around, for the data, we have around 2,000 samples, and of course in virtual reality. And then on the real robot, for testing the sim to real transfer, we have around 180 samples. So we have the Tiago robot, and we have the UR3 with a gripper. And the model, the prior is basically the same. It's exactly the same prior. Then we say, okay, let's move to a more complicated example, and then we were inspired by Daniel's dropping part. And here we say, okay, let's add more variables. And of course, the complexity of the problem is now different containers. And let's see if we can actually also observe similar in the prior and the real symptom transfer. In numbers, they're more or less the same. Of course, the structure is more complicated, right? This is what it's looking like. So the robot is now executing the task. Of course, we always command the robot to go to the best position, right? But due to whatever problems on the accuracy of the controller or the perception, there will be always some misalignment. And this is basically what is explained here. So this is the virtual reality scenario that we collect all the samples. This is what I explained before, the sim to real transfer. And it was interesting to see that at some, it was around 70%, so it's okay. I mean, things we can learn from prior information from virtual reality is able to be transferred to real robots. And now this one, this is the model, and it's using contrastive search to actually find out, at this point, the robot will fail. But once it fails, it will produce an explanation, saying, hey, I failed because I drop it too much to the right, too much to the left, or depending on the parameters, so using this contrastive search. Now we have the second scenario, right? And then the problem is, what was the problem? Was it the last cube? So for this, the robot needs to have some kind of memory as well, right? So it has to have this representation, and then it has to have some kind of memory. And for that, of course, we have a more complicated problem, so we can have a more rich structure. And if you think about it, the second cube is even more complex than stacking the first cube, because you depend on the first cube to be correctly stacked, right? This is something we didn't thought about, but when we saw it, I was like, yeah, I mean, makes sense, right? So what is happening now is the system is at each step analyzing, okay, what is my success of continuing if I know that I have to build a tower of 4 cubes? Then it's doing the contrastive search, and it's finding, hey, this parameter is the one you are going to execute. Don't instead use this parameter. And this is basically how we are trying to help the robot to actually predict that there is going to be a failure and then fix it. So we have 2 scenarios. In both scenarios, of course, as you can imagine, it's going to fail. So this is basically to explain, and we have 2 models, because we say, okay, what about if we don't want to use all the different variables and we want to use one single model? It's possible, but the problem is you will not remain this kind of memory you need. For the memory, you need all the different variables, right? Then we have this Bayesian network that is going to predict, okay, at this point, this was not correctly aligned because whatever problem. And then this is the one model that I was telling you, and this is the 3 model that I was telling you. This is the one we obtained from the previous example, right? And now here, you see the robot is obtaining, okay, this is wrong, I need to fix it. So now it's going to fix it, hopefully, yes. Now it succeeds, right? And this one is very interesting, because when I saw the video, I thought, no way, it's not going to hold the tower. But yes, it's doing it, right? So it was able to predict, and what we are currently working on is, we know these Bayesian network algorithms, they require a lot of data. And then we say, okay, what about if we can transfer learning and disseminate that into the next problem? Because we could see it as an iterative problem, right? And this is basically what we are working on. How can we transfer this prior experience into let's say, the second step? What are we working on is, okay, how can we move from household to now industrial scenarios? And for this, we have a very nice collaboration with Volvo. And we are now including the human in the loop. Now we have collaborative robots. And we are looking at maintenance base, so we want to help technicians to help changing the tire. Of course, we'll not be able to change the whole tire, but we are looking at unscrewing the tire. This is these changing tires, it's a procedure that you need for all kind of maintenance from trucks. So if we manage to help humans here, will be a very good success. Of course, we cannot stop the production line in Volvo for trucks, so we need to start building a digital twin. So, and that of course we need to include the robot, and we need to do all the dynamics, and we're still working on it. We don't have a very nice, successful paras like that. But then you see, now we're talking about collaborative robots. That means challenges are going to increase a lot. First, we need to recognize collaborative tasks. It's not the same when you are alone doing the task, when you are collaborating with others. You need to predict what the other is going to do. Next, we need to physically interact with the other robot. So we need to address that problem of physical interaction. And finally, you need to also know how to communicate with the robot. How many times you want to hear the robot telling you, hey, you're going to be wrong. Hey, you're going to be wrong. Probably not that many, right? So we need to know what is the right strategy, what is the right message, how often, etc. So there are a lot of challenges we are working on right now. And yes, to conclude my talk, so we're working on different parts of the reasoning part, which is basically on semantic base. So we have different abstraction layers. I didn't have the time to talk about that today, but we do have those. And now we are including failures into this semantic layer. We also connect with the ontologies. We were using a very previous early version of NOROP. Right now, we don't know what is the stage of NOROP, but hopefully we will collaborate. And then, of course, the failures, and next we are now looking into reinforcement learning maybe for the parameter of the execution of the robot. Yes, of course, I need to acknowledge everyone behind that. So we have PhD students, and we have a student that is helping us with the VR, and in the summer we have a very nice type of students, and this is the project we have with Volvo and some national and international collaborations. Thank you.
Yeah, thanks a lot, Karin, for that cool talk. And yeah, we are now at the end of the scientific program here. And yeah, take some time and go into the labs and have a look around what we have to offer in the different areas. And yeah, so the doctoral students look forward to your visit and are ready to discuss. Thanks.